You know, when you picture a major IT outage, you probably imagine this sudden cinematic explosion, right? Alarms instantly blaring, screens flashing red everywhere, people running around, everything just stopping all at once. But in reality, production systems rarely explode instantly like that. It's usually a lot quieter.
Instead, it looks a lot more like a slow, creeping timeline. First, it's just minutes passing by. Your CPU slowly creeps up to, say, 90%. No big deal, right? Then hours go by. Latency starts increasing by a few hundred milliseconds, and a background queue starts quietly backing up. A few more hours pass, and your logs are literally screaming with warnings, but nobody notices. Finally, the system just quietly flatlines. And you know what the real emotional pain is here? Your team only finds out because angry customers are flooding your support channels, complaining about downtime and lost money. That hurts.
And this brilliantly illustrates what we call operational blindness. Think about it. You actually had the data. Your infrastructure was actively begging for help. But because you lacked the automated awareness to translate that data into actual action, you missed every single warning sign. Listen, as a SysOps administrator, curing this exact blindness, that's your entire job. You have to be the one who opens the team's eyes.
Let's break down the core difference between proactive and reactive operations. Think about flying a massive commercial airliner. You definitely don't wait until the engines literally shut off mid-flight to realize you're out of fuel, right? Of course not. You fly proactive operations. You have a massive dashboard right in front of you, full of dials and indicators. If the cabin pressure drops even a fraction of a percent, a warning light flashes, a buzzer sounds, and the pilots react instantly. Reactive operations, on the other hand, well, that's like taping a piece of cardboard over that airplane dashboard and just hoping for the best. I know it sounds completely absurd, but that is exactly what operating an infrastructure environment without proper monitoring is like.
So how do we rip that cardboard off and uncover what's actually happening inside our architecture? Well, you need the 3 pillars of observability. First up, we have metrics. Think of metrics as your pulse. They are time-ordered data points, things like CPU utilization or network traffic that tell you that a system is sick. Second, we have logs. Logs are your diary. They're the immutable records of exactly what happened. If metrics tell you that you have a problem, logs are going to tell you why you have that problem. And third, traces. Traces are your roadmap. In modern distributed systems, a user request jumps all over the place. A trace follows that exact request step by step so you can see exactly where the bottleneck is hiding.
Now there is a massive trap here, and I really need to point this out. If you are digging through logs to find out why a server died, the outage has already happened. This is where people mess up. A huge trap that engineering teams fall into is treating monitoring as an afterthought and relying completely on logs. Remember, logs are historical. If you're relying on them as your primary monitor, you are discovering the failure from your customers first. And that is an entirely reactive way to operate.
So how do we fix this? Well, in AWS environments, the answer is Amazon CloudWatch. Now, CloudWatch isn't just some optional add-on. It is literally the central nervous system of your environment. It centralizes your logs, it ingests your metrics, and it builds customized dashboards. But here is the catch. Out of the box, CloudWatch is really just collecting numbers. It's entirely up to you to tell it what actually matters to your specific application.
And that is exactly where CloudWatch alarms come in. Instead of paying someone to just stare at graphs all day long, you set up a tripwire. You tell CloudWatch, hey, if the CPU on this instance stays above an 80% threshold for 5 minutes straight, do something. The moment that threshold is breached, the alarm flips its state from OK to alarm. Think about that for a second. An alarm isn't just a passive notification. It is an active, automated response mechanism.
So the absolutely crucial point here is that we don't just want to wake an engineer up at 3 in the morning. Nobody wants that. We want automated remediation. When that alarm flips, it should immediately trigger an auto-scaling policy to add more instances to handle the load. Or it could execute a systems manager automation runbook. Or maybe it automatically recovers a frozen EC2 instance. The whole point is that the system fixes itself before a human ever even opens their laptop.
But what happens if the system fails so completely that it just stops sending data entirely? Well, CloudWatch lets you specify exactly how to handle missing data points. A proactive approach is configuring your alarm to treat missing data as a breach, basically treating silence as bad news. If you choose the blind approach, which is leaving the alarm in its previous state, your instance could die entirely, taking all its metrics with it. Your alarm stays green, and you remain completely blind to a massive failure.
Without that automated awareness, a tiny, localized glitch easily turns into a catastrophic resume-generating event. Imagine a massive e-commerce site during a huge holiday traffic spike. Step 1. One backend instance silently runs out of memory and freezes. Step 2. Your load balancer sees it failing health checks and abruptly shifts all that massive traffic to the remaining healthy servers. Step 3. Now those healthy servers are carrying an absolutely impossible load, so their CPU spikes and latency jumps from 50 milliseconds to 5 whole seconds. Step 4. The whole stack collapses like dominoes. Everything just goes down.
All right, let's slow down, step back, and look at the solution here. How do we actually catch that spark before it burns the whole building down? Well, if you had installed the CloudWatch agent on your instances and set up an alarm specifically watching memory utilization, that alarm would have triggered early. You could have proactively terminated that one bad frozen instance before it ever had the chance to bring down your entire fleet.
And really, this is the ultimate embodiment of the proactive SysOps mindset. We don't just build systems, we build systems that survive. We anticipate failure at every single turn. We instrument our applications with monitoring before they ever go live, not after. We set precise thresholds based on real, actual behavior, and we design alarms that trigger automated remediation to fix the issue long before the customer ever clicks refresh.
Listen, your infrastructure is always talking to you. The metrics are pulsing, the logs are writing, and the traces are flowing. But here is the ultimate question you have to ask yourself. When your system finally screams for help, are you actually listening?
Okay, let's dive right into this explainer. I want you to picture this. It's 3 a.m. Your phone is literally vibrating off the nightstand. It's the exact sound every single operations engineer absolutely dreads. And you know before you even open your eyes that your night is officially over. You were in a deep sleep, and now adrenaline is just spiking. Is it a minor glitch, or is the entire platform down? The uncertainty in those first few seconds is absolutely brutal. You wake up, you're completely confused, just squinting at that painfully bright screen. And there it is. You have 47 unread Amazon SNS notifications, your automated texting service, completely clogging up your lock screen. Half your infrastructure is screaming that it's in an alarm state. Production is in total chaos. It's not just one isolated service. It looks like everything is failing all at once. The database, the load balancers, the cache, they're all just flashing red. When you're hit with this massive barrage of data at 3 a.m., your brain can't even process it. You're just staring at a wall of absolute panic. So what do you actually do, honestly? Let's be real. A lot of engineers just mute their phone, roll over, and go right back to sleep. And why do they do that? Because out of those 47 alerts, 46 of them were probably just useless noise, just transient spikes that'll resolve themselves in a minute anyway. But here is the terrifying part and the real danger of this whole scenario. Somewhere buried deep in that pile of false positives, a real outage is silently taking down your production database. When everything is an emergency, literally nothing is an emergency. The useless noise completely masks the actual fire. In AWS environments, Amazon CloudWatch alarms are how you detect that failure before it becomes a full-blown disaster. They're the eyes and ears of your infrastructure. But here's the harsh reality. Bad alarm design creates just as much operational blindness as having no alarms at all. Let's break this down. At its core, an alarm is simply a tripwire. It watches a specific metric, like CPU usage, memory consumption, or network traffic, and if that metric crosses a predefined line, it automatically acts. It sends a message, pages an engineer, or triggers a script. But think about a physical tripwire for a second. If you set that tripwire way too low to the ground, you're going to trip over it every single time you walk into the room. It just becomes a frustrating obstacle, not an actual security measure. CloudWatch is constantly evaluating your system metrics, and every single alarm rests in one of 3 states. First, you have OK. If the metric is fine and within bounds, you're in the OK state. Green lights, everything is happy. Second, if it crosses that tripwire threshold we just talked about, you immediately hit alarm. Red lights, sirens going off. But the third state is uniquely important. It's called insufficient_data. If the system stops reporting data entirely, maybe the CloudWatch agent on your server crashed, or perhaps a brand new service just hasn't collected enough data yet to form a baseline, you shift into this state. This is absolutely crucial because it lets you know your monitoring itself might actually be broken. It's the system literally saying to you, hey, I can't even tell you if things are okay right now. But here is where real-world operations teams fall into a very dangerous trap, setting dumb, static thresholds. Imagine you set a hard-coded alarm to trigger anytime your CPU hits 90%. Makes sense, right? High CPU is bad. But what if your application runs a heavy batch processing job every single morning at 9 a.m.? It intentionally spikes the CPU to crunch those numbers. With a static threshold, your on-call engineer gets paged every single morning while they're pouring their coffee. The pager goes off, they groan, they open their laptop, and they quickly realize, oh, it's just the standard batch job. So they ignore it. This is the absolute fastest path to alarm fatigue. When you drown engineers in false positives, they stop paying attention. They learn to ignore the system. Think about that for a second. What happens when a real outage actually occurs at 9 a.m.? They ignore that page too, assuming it's just another false alarm. To fix this fundamental flaw, CloudWatch gives you a really powerful tool, anomaly detection. Now, this is where things get really smart. Instead of relying on a hard-coded number you just guessed on day one, CloudWatch applies machine learning to your past metric data. It continuously analyzes days or even weeks of history to establish a baseline and learn what normal actually looks like for your specific application. It learns that the 9 a.m. CPU spike isn't an error at all. It's a completely expected daily rhythm. So you tell the alarm to trigger only when the metric deviates outside the statistically expected band. If CPU hits 90% at 9 a.m., it stays totally quiet. But if it hits 90% at 2 p.m. when it should be entirely idle, boom, alarm. Suddenly, the false positives just vanish. The noise stops. Now, let's shift gears and talk about the ultimate nightmare scenario: alert overload and cascading failures. Imagine a localized database failure. If your primary database locks up, the damage doesn't stay neatly contained. No, it cascades instantly across your entire architecture. Your web servers start throwing 500-level errors because they can't query data. Your elastic load balancer latency spikes drastically because user requests are just queuing up endlessly. Your cache nodes run completely out of memory trying to compensate. If you have separate, independent alarms for every single one of these metrics, the on-call engineer is going to get hit with 50 different SNS notifications at the exact same second. Your phone is literally vibrating off the desk. You are drowning in alerts. You can't even begin to troubleshoot the root cause, which is the database, when you're overwhelmed by that much sheer panic and noise from all those downstream symptoms. To survive this kind of catastrophic overload, sophisticated SysOps engineers use something called composite alarms. A composite alarm doesn't watch a metric directly. Instead, it watches the states of multiple other alarms and uses simple Boolean logic like and, or, and not to figure out if it should actually page you. It rolls up the symptoms. For example, you can set a rule that says, only send a critical alert if the database CPU alarm and the web server error alarm are both firing simultaneously. This tells you there's a real system-wide impact. Or you can use a not rule to be even smarter. You could say, alert me if the database fails, but not if it's currently inside a scheduled maintenance window. By grouping these together, this immediately kills the noise. The result here is honestly transformative. Instead of a massive flood of panic, you get one highly accurate, highly actionable alert. It points you directly to the system-level problem. And the beauty of the AWS ecosystem is what happens next. Because these composite alarms integrate directly with Amazon SNS, you can route that single critical alert to an external on-call paging system. But even better, you can trigger an automated Lambda script to take immediate action. You can have that Lambda function automatically restart a stalled service, clear a bloated cache, or seamlessly fail over to a backup database in a completely different region. The system actually starts healing itself before a human being even has time to open their laptop. So what should you really take away from this explainer? Look, monitoring isn't just about collecting terabytes of raw data or drawing pretty complicated graphs on a dashboard. It's fundamentally about designing a system that speaks up loudly when it matters and stays dead quiet when it doesn't. Because in operations and infrastructure, silence is only valuable when the system is actually healthy. If your system is quiet because your alarms are broken or because your engineers have completely muted their notifications due to fatigue, that is terrifying. A missed alarm doesn't just create downtime. It creates massive operational blind spots where you are actively losing money, you're losing customers, and you don't even realize it's happening. At the end of the day, you want your team to jump into action the absolute second an alert fires, with full confidence that it's real. The best alarms, the ones that actually protect your business, are the ones engineers trust enough to never ignore. Every single page should mean something. So I want to leave you with this thought. Look at your own infrastructure, your own dashboards, and your own phone at 3 a.m. How much do you actually trust yours? Welcome to this explainer, the black box, where we're going to master operations with CloudWatch logs. Let's just dive right in. I want you to imagine the absolute worst-case scenario. It is 2 in the morning, your systems are completely down, you are facing massive downtime, and your company is hemorrhaging money by the second. Customers are angry. Twitter is lighting up. Your dashboards are flashing red everywhere you look. They are showing CPU spiking completely out of control. and this massive, terrifying wave of 500-level errors is rolling in. The sheer panic is setting in. Everyone on the team is frantic. They're staring at the metrics, sweating, just trying to guess what on earth went wrong. But right here, this is where we need to take a breath and realize something absolutely crucial. Metrics only tell you that the system is sick. They are the what. They do not tell you the why. Then a senior engineer bypasses the flashing dashboards and goes straight to the logs. And there it is. The database connection pool had been exhausting itself. It was quietly throwing warning errors for 3 entire days before the complete crash. The evidence was sitting right there. The system was trying to warn you, but nobody looked. Think about a commercial airliner crash. Investigators don't just look at the broken pieces scattered on the runway. No, they search for the black box flight recorder. Logs are the exact same thing for your AWS infrastructure. They are the immutable records of discrete events, capturing exactly what happened, complete with a precise timestamp. If you want to know why a catastrophic failure occurred, you absolutely have to read the flight recorder. In AWS, that black box is Amazon CloudWatch Logs. CloudWatch Logs enables you to centralize the logs from all of your systems, all of your applications, and your AWS services right into a single, highly scalable service. It's your ultimate centralized destination. But to actually use this data effectively during a high-pressure outage when literally every second counts, you have to understand how it's organized under the hood. So, under the hood, this breaks down into 2 core concepts. First up, we have the log stream. A log stream is basically a sequence of log events that share the exact same source. So the crucial point to remember is if you have a single Amazon EC2 web server or maybe a single Lambda function, it writes its data into its own dedicated log stream. It is a continuous, ordered sequence of events from one specific place. But let's be real, looking at just one stream doesn't really help when your application is running across 50 servers, right? This is exactly why we use log groups. A log group defines a collection of log streams that share the exact same retention, monitoring, and access control settings. And the best part? There is absolutely no limit on the number of log streams that can belong to a single log group. You just bundle those 50 web server streams into one logical log group so you can search them all at once without hitting any walls. Now, listen closely because this is where people mess up. This is a massive trap that so many teams fall into. Imagine an outage hits. Your architecture spans multiple AWS accounts and multiple regions. If your engineers are manually logging into individual servers, if they are tailing text files blindly via SSH, or frantically jumping between 12 different AWS accounts just to find a single log entry, it is already too late. Your downtime is skyrocketing. This manual approach is a disastrously slow way to operate during a real fire. Modern operations teams just don't search manually. Instead, they use cross-account, cross-region log centralization. CloudWatch Data Centralization works directly with AWS organizations to collect log data from multiple member accounts into one single centralized data repository. You basically define rules that automatically replicate log data from all your source accounts into a central monitoring account. So when the fire starts, your team goes to one place, one unified dashboard to find the absolute truth. And during an operational investigation, you aren't just scrolling blindly through endless walls of text. You use CloudWatch Logs insights to interactively search and analyze your log data. You can write a quick query to instantly parse out every single log event tied to a specific failed request ID. You can cross-reference your database timeouts with your web server errors. And what's really amazing here is you can use Livetail to view a streaming list of new log events as they are ingested in near real time. This helps you instantly validate if the fix you just deployed actually worked. But what happens if you go to query that crucial log data and it is completely gone? Think about that for a second. This is what we call the missing evidence trap. And trust me, it happens all the time due to mismanaged retention policies. Let's break down this timeline so you can see exactly how it happens. By default, CloudWatch Logs keeps your log events indefinitely. But as we all know, storing terabytes of log data forever gets incredibly expensive, right? So teams configure a retention policy to automatically delete log events after a specific time frame, let's say 14 days, just to save some money. But what if a silent security breach or settled data corruption happened on day 1, and you don't even discover the outage until day 20? Your logs from the incident are automatically deleted on day 14. You have no crime scene, you have no evidence, you just created a permanent operational blind spot for yourself. This is a massive trap, both in real-world production and if you're taking your AWS exams. The biggest mistake engineering teams make is treating logs like a graveyard. They only bother to look at them after the system is already dead. They rely entirely on top-level metrics, totally ignoring the fact that their application logs are actively writing warnings, timeouts, and retries right now. We have to make the ultimate operational mindset shift here, moving from a reactive graveyard to active monitoring. We don't just store logs to read them later, we actively listen to them in real time. So how do we actually do that? Well, we assign metric filters to our log groups. This automatically extracts metric observations from ingested events, turning raw text logs into actionable data points. Step 1, ingest the log event. Step 2, your metric filter looks for specific words. If the word exception or timeout suddenly spikes in the logs, that filter catches it. Step 3, it instantly triggers a CloudWatch alarm. You don't wait for the server to crash, you don't wait for the customer to complain on Twitter, you know before they do. Your infrastructure is never truly silent. Your logs are always trying to warn you. The only question is, are you investigating the clues or are you waiting for the crash? Take a moment to reflect on your own infrastructure. Welcome to This Explainer. Look, today we're tackling a challenge that absolutely keeps cloud architects and developers wide awake at night. We're going to talk about debugging modern cloud architectures. You know, as our systems get more advanced, they also get incredibly complex. And when things go wrong, finding the root cause can feel exactly like searching for a tiny needle in a massive digital haystack. So today, we are navigating distributed chaos and unlocking the power of AWS X-Ray. Imagine this scenario for a minute. Your pager goes off. Customers are reporting failures. Checkout is completely broken. Your company is literally losing money by the second. Take a moment and let that real-life nightmare scenario sink in. Okay, so you look at your API gateway metrics, and sure enough, error rates are spiking fast. Naturally, you panic slightly, right? You immediately check the database metrics, but they look totally fine. CPU is normal, memory is completely stable. So you start frantically digging through CloudWatch logs, desperately looking for a single clue. But here is the agonizing reality of modern cloud setups. Your architecture isn't just one single server anymore. It's an API gateway, which triggers an AWS Lambda function, which then puts a message on a queue, triggering another Lambda, which finally updates a database. The logs exist, sure, but they're scattered across dozens of completely isolated microservices. It all leads to this incredibly frustrating realization. A request entered the system, and nobody knows where it died. This is exactly why distributed systems become almost impossible to debug if you aren't prepared. Let's slow down for a second and really look at the contrast here. Back in the old days of monolithic applications, everything happened in one place. If something broke, you simply logged in and checked that one server. Easy. But in a modern architecture, a single customer click hops across 5, 10, or even 20 different AWS services before it actually finishes. You completely lose visibility in the empty spaces between those systems. When you're debugging issues in a microservices architecture, you absolutely have to find a way to trace a single transaction across multiple disconnected services. Okay, let's dive into this. Think about it like this. How do you track a lost package through a global shipping network? If a package goes missing, you don't just pick up the phone and start randomly calling warehouse managers in 5 different countries asking if they've seen a brown box, right? That would be completely chaotic. It's impossible. Instead, what do? You use a tracking number. A tracking number is brilliant because it gives you the exact timeline. It tells you, hey, your package arrived at facility A, it left facility A, and then it mysteriously vanished on the truck heading to facility B. You know exactly where the chain broke. While in AWS, that tracking system is AWS X-Ray, and the practice of doing this is called distributed tracing. X-Ray gives you true end-to-end operational observability. It does this by tracking a user request from the very beginning to the very end as it travels through your entire infrastructure, no matter how many different services it touches along the way. Now, what's really interesting about this slide is how X-Ray actually breaks this down under the hood. When a request hits your very first service, X-Ray generates a unique trace ID. That trace ID represents the complete journey of the package. It's your overarching tracking number. But as the request hops through your architecture, say hitting a Lambda function, the logs will automatically record that specific X-Ray trace ID alongside a local X-Ray segment ID. That segment ID documents exactly what that specific service did, the exact time taken, and whether it threw any errors. And once all those hops are complete, X-Ray just does the heavy lifting for you. It automatically stitches all of those individual segments together into a single cohesive timeline. It builds the complete picture of your request's journey. No manual sorting required. Now, here's where distributed systems become terrifying. I really want to warn you about the isolated logging trap. This is a massive trap, and honestly, this is where people mess up both in real production outages and, by the way, it's a classic trap on your AWS SysOps exam. People try to debug microservices using only isolated logs. But remember, requests are hopping across multiple services concurrently. You simply cannot rely on isolated logs alone when you're dealing with concurrent distributed microservices. Think about that for a second. If a checkout takes 10 seconds, where exactly did the time go? Latency spreads across dependencies. Your front-end API might time out, but the actual root cause could be a 4,000 millisecond bottleneck hidden 3 layers deep inside the architecture. Sure, you could try to manually write queries to join logs from 2 different services using a common transaction ID, but doing that manually during a massive outage, it is incredibly slow, it is highly stressful, and it is entirely reactive. And this brilliantly illustrates where X-ray service maps just change everything. X-ray takes all of those traces and automatically draws a visual map of your entire architecture. It shows you the nodes, the connections, and the exact flow of traffic. More importantly, it eliminates all that reactive guessing by color-coding failures and explicitly highlighting latency bottlenecks. You aren't guessing anymore. You look at the visual map and you immediately see the health of your system. Your web server is green, your authentication service is green, they are perfectly healthy. But right there in the middle, the connection to the payment API is glowing red and taking 4,000 milliseconds. The failing node is instantly, undeniably visible. So in a real-world debugging workflow, a SysOps engineer doesn't panic when a distributed system fails. You just follow this simple process. Step 1, you open the service map. Step 2, you spot the bottleneck visually. Step 3, you click on that glowing red node. And step 4, you view the specific traces that are failing. You see the exact segment where the latency spiked, all without breaking a sweat. And honestly, it gets even better. If your infrastructure is massive and spans multiple AWS accounts, you can actually set up CloudWatch cross-account observability. This is an incredibly powerful feature that allows you to seamlessly search, visualize, and analyze nodes from multiple source accounts directly inside your single X-ray trace map. You get all your metrics, logs, and traces in one place, totally unbothered by account boundaries. Section 1. Designing for visibility. So, the crucial point is you cannot manage a modern cloud environment by treating it like a collection of black boxes. You need an action plan for engineering maturity. You absolutely must instrument your code. You need to ensure you pass your trace headers downstream. You have to build systems from the ground up that leave a clear, undeniable trail of evidence. This is exactly how you achieve proactive visibility instead of reactive panic. Because in a distributed system, a failure isn't actually the worst thing that can happen. Hardware fails, code has bugs, failures are just a given. The worst thing that can happen is a failure that you can't even find. Thank you for joining me on this explainer. Start instrumenting your code, embrace X-ray. Okay, let's dive right into this. Welcome to today's explainer, where we're looking at something that fundamentally changes how we handle cloud operations. We're talking about self-healing infrastructure and exactly how to turn your AWS environment into its very own automated first responder. Let's set the stage. Picture this scenario. It's 4 a.m. on a Saturday. You are fast asleep. Suddenly, a critical backend Amazon EC2 instance running your application becomes impaired. Why? Because the underlying hardware just completely failed out of nowhere. Instantly, your application starts throwing errors and your metrics spike off the charts. But your engineering team is sound asleep. Nobody is logging in manually. Nobody is frantically scrambling through outdated wikis trying to find the right runbooks. And yet, 5 minutes later, a minor miracle happens. The instance comes back to life. The application completely stabilizes. By the time you actually wake up and check your phone hours later, the outage is already over. The system literally fixed itself before anyone even touched a keyboard. Now, this scenario brilliantly illustrates a very hard truth about modern cloud environments. When production breaks, relying on a human to wake up, open a laptop, parse through logs, figure out what died, and then manually restart a server, that is a massive operational failure. Manual recovery is simply too slow during a real outage. Every single minute an engineer spends typing commands is another minute your company bleeds money. Section 1. The paradigm shift. Rethinking incident response. Let me give you an analogy here. Think about a building on fire. You don't want to wait for the fire department to wake up, jump in a truck, and drive all the way across town just to start putting it out, right? By then, the damage is done. Instead, you want the ceiling fire suppression system to activate the exact second smoke is detected. Your infrastructure needs that exact same automatic suppression system. Think about that for a second. Waiting for a human is like waiting for that fire truck. Section 2. Defining infrastructure health. Now, let's slow down here for a minute because this distinction is incredibly important. In AWS, your instances are constantly being monitored by two distinct types of status checks. First, we have instance status checks. These look for software and network issues happening inside the virtual machine itself. Second, we have system status checks. These look for underlying hardware failures. So if the power or the network connection to the physical host actually goes down, that system status check immediately fails. Section 3, the auto recovery solution. Now, listen closely because this is where people mess up. Here is the classic trap. When a system status check fails, engineers often panic and manually force a reboot. Or even worse, they just build a CloudWatch alarm to send them an email alert so they can log in and try to fix it manually while they're half asleep. But AWS actually has a brilliant built-in feature that most engineers completely forget to configure. It's called EC2 Auto Recovery. You can create a CloudWatch alarm that watches that exact system failure metric we just talked about. But instead of paging a human, you tell the alarm to execute an automated recovery action. What's really interesting is what happens next. When that alarm triggers, AWS automatically migrates your instance to new, healthy hardware. And it does this while keeping the exact same instance ID, the same private IP addresses, the same elastic IP, and all the same metadata. The server died and it literally brought itself back to life identically. Of course, self-healing extends way beyond just single instances. If you're running an auto-scaling group, it's constantly performing periodic health checks. And if you enable elastic load balancing health checks, the moment your application stops responding to traffic, the load balancer reports it as unhealthy. The auto-scaling group then immediately terminates that bad node and launches a brand new one to replace it. Again, all without you ever touching a keyboard. Section 4. Beyond the instance, deep remediation. Because recovering a dead instance is great and all, but what if your application process crashes? What if your disk fills up? Or a critical security configuration drifts over time? You need deep remediation automation. You need the system to react to those complex events as they happen in real time. Enter Amazon Event Bridge. Think of Event Bridge as the central nervous system for your automated responses. It listens to a continuous stream of events across your entire AWS environment. When an instance fails a health check or an auto-scaling group drops a node, EventBridge catches that exact event the precise millisecond it happens. But EventBridge is just the trigger. To actually fix the problem, EventBridge passes the baton to AWS Systems Manager automation. Systems Manager acts as the hands here, using predefined workflows, which we call Runbooks, to perform precise automated steps to resolve the issue. So the crucial point is how this all flows together. Let's say a specific background process freezes. A CloudWatch metric detects the freeze, triggers an EventBridge rule, and that rule immediately executes a Systems Manager runbook. That runbook securely connects to the node, restarts the service, flushes the cache, and verifies the application health. You didn't just reboot a server, you performed a highly specific multi-step operational fix, completely hands-free. Section 5. The automation mindset. You see this all the time. Teams build massive monitoring dashboards. They set up complicated alerts. They do all the hard work to detect the warning signs. And then they leave the actual recovery up to a stressed, sleep-deprived human being who has to manually run scripts at 3 in the morning. Building alerts without automated recovery is really only doing half the job. You have to shift your downtime mindset. The goal is no longer just to fix the system when it breaks. The goal is to build a system that fixes itself. You need to instrument those health checks, define your EventBridge rules, and author your Systems Manager runbooks. You are turning the infrastructure into its own first responder. I want to leave you with this final thought to take away from today's explainer. In a modern cloud operations environment, the best engineer isn't the one who fixes the outage the fastest. It's the one who builds a system so resilient, nobody even knew it broke. Picture this. It's 3 a.m. and your phone rings. Only, it's not a text from a friend. No, it's that automated voice telling you production is down. So you drag your laptop open, your eyes are absolutely burning, and you jump straight onto the emergency bridge call. There are already 6 other engineers on the line, customers are just flooding support with complaints, and everyone is talking over each other. You pull up your Amazon CloudWatch dashboards, and man, the screens are literally bleeding red. The CPU is pegged, database connections are dropping fast. But here's the worst part. Nobody on the call immediately knows the root cause. Those alerts woke everybody up. And now, the team just has to survive the outage. Welcome to incident response, folks. If you work in ops, you've definitely been here. In the dead of night, production incidents are just pure, organized chaos. The pressure is completely suffocating.
Because every passing minute means lost revenue, broken trust, and seriously escalating panic. But navigating this exact scenario, that's exactly what separates junior administrators from true senior SysOps engineers.
Section 1. The Trauma Protocol, Operational Maturity in AWS. Think about an emergency room trauma team for a second. When a patient crashes, the doctors don't just stand around arguing about how the human heart works, right? And they definitely don't try to invent some brand new surgical technique right there on the spot. Instead, they run a trauma protocol. Everyone in that room knows exactly who is in charge. Everyone has a very specific role. They follow a strict, predefined checklist just to stabilize the patient. Well, your AWS environment requires that exact same level of operational maturity. When an alarm triggers, the absolute worst monitoring strategy is blasting out a generic email to 50 different engineers and just hoping someone claims it. Doing that just creates a massive bystander effect. Instead, mature operations teams use AWS Systems Manager Incident Manager. Incident Manager defines exactly who gets paged first. It's totally structured. If the primary on-call engineer doesn't acknowledge the alert within, say, 5 minutes, it automatically escalates to the secondary engineer and then right on up to the operations manager. So there is zero ambiguity about who actually owns the problem and who is actively investigating it. But listen, getting people on a call is really only step one. Once they finally arrive, they need immediate visibility into the system. During a major outage, you absolutely do not have the time to manually write custom CloudWatch logs insights queries from scratch. You also don't have time to click through 20 different AWS services just trying to piece together what went wrong. What you really need are purpose-built CloudWatch dashboards. But here's the real catch. A dashboard is entirely useless if it doesn't have clear ownership. If an engineer looks at a graph during an active outage and says, "I don't really know what that line means," well, that dashboard has completely failed you. Your dashboards really must be designed specifically for incident response. They need to immediately highlight that strict boundary between healthy and unhealthy systems. You should be able to see it at a single glance. Now, this is exactly where immature operations teams completely fall apart. When an outage hits, immature teams improvise. They just start manually restarting instances. They blindly modify database configurations. They even apply hotfixes directly to production without testing them first. Ultimately, they are just guessing. In the real world and heavily tested on your SOA-C02 exam, by the way, improvising during an outage is incredibly dangerous. I really want you to think about that for a second. You should never, ever be guessing at 3 a.m. Instead, you need to rely on operational runbooks. A runbook is simply a documented, step-by-step procedure designed to resolve a very specific issue safely and effectively. So if your database connections max out, the alarm shouldn't just wake you up. It should actually link you directly to a Systems Manager automation runbook. That runbook tells you exactly how to safely drain those connections, or even better, it executes the fix for you completely automatically. Because honestly, firing an alert without attaching a runbook is essentially just paging an engineer to tell them to panic. And our goal here is to eliminate that panic entirely. Why? Because every single action you take during an incident has one singular goal: reducing your MTTR. That's your mean time to resolution. Look, when you have way too many alarms, engineers naturally get alert fatigue and they start ignoring the warnings. When you have no clear escalation procedures, so much time is wasted just trying to find the right person to look at the screen. And when engineers are forced into improvising, that's when MTTR stretches from a few minutes into agonizing, painful hours. Section 2. Systems Manager Ops Center. Stopping the clock. Tools like Systems Manager Ops Center are designed entirely around stopping this clock. Ops Center aggregates all your operational work items, which AWS calls ops items, and it standardizes the investigation data. So your team isn't just frantically bouncing between browser tabs. It attaches the history, the related resources, and those automated runbooks right there in a single pane of glass for you. This right here is the fundamental difference between reactive panic and proactive control. Mature cloud operations teams can handle outages calmly simply because they have already practiced failing. They already know their escalation paths. Their alarms are finely tuned to avoid those annoying false positives. Their runbooks are written, heavily tested, and integrated directly into their incident response plans. You see, as an AWS SysOps administrator, you really have to fundamentally shift your operational mindset. Your goal isn't to build a system that literally never breaks. That's impossible. In a distributed cloud architecture, everything fails eventually. Your actual goal is to build an operational culture so mature and an incident response workflow so completely controlled that when the system finally does break at 3 a.m., your team doesn't panic. They just execute. So I want to leave you with a question to ask yourself. When your phone inevitably rings tonight, will you be calmly running a protocol or will you just be guessing?
Welcome to this explainer on architecting for survival, regional resilience, and disaster recovery. Let's dive right in.
Dashboards are disappearing. Your APIs are throwing 504 gateway timeouts. You jump into your incident response channel, right? You're assuming a database crashed, or maybe a critical server failed. But as your team starts digging, that cold sweat sets in. It isn't just one server, it's all of them. The load balancers are unreachable. The subnets are dark. The databases are gone. You haven't just lost a server, the cloud just lost an entire city.
Section 1. Regions versus Availability Zones. Understanding the blast radius.
You know, when an entire AWS region goes down, it really is the ultimate test of your operational maturity. To survive this, you have to fundamentally understand how AWS is physically built. An AWS region is a physical location in the world where AWS clusters its data centers, which are known as availability zones. Think of an AWS region like a massive metropolitan city, and the availability zones, those are the distinct, isolated neighborhoods right within that city.
Each availability zone has its own independent power, its own cooling, and its own physical security. Plus, they're physically separated by a meaningful distance. So if a tornado, a massive flood, or an errant backhoe wipes out one neighborhood, the other neighborhoods stay online. This right here is the absolutely crucial core concept of fault isolation.
When you partition your applications across multiple availability zones, you're isolated and protected from localized physical disasters. If an availability zone suddenly drops offline, an application load balancer can just stop routing traffic to the bad zone, while an auto-scaling group automatically redistributes your application instances evenly across the remaining healthy availability zones. So with availability zones, you can design and operate applications that automatically fail over between zones, literally without interruption.
Section 2. High availability is not disaster recovery, avoiding the massive trap.
Now, here is where companies discover whether they actually designed for resilience. This is where people mess up. A massive trap that engineering teams fall into is confusing high availability with disaster recovery. Multi-AZ architecture is high availability. It protects you against the loss of a single neighborhood. But what happens if an unprecedented, catastrophic event takes out the entire city? What if the entire AWS region goes dark?
Assuming an AWS region will never fail is a massive operational blind spot. If you only deploy in a single region, you don't actually have a disaster recovery plan. You're really just hoping for the best. To guarantee business continuity, you absolutely must build multi-region architectures.
Section 3. Architecting for regional failover. Design from day one.
Disaster recovery means that when your primary region completely fails, your business survives because you have a secondary, geographically distant region ready to take over. But, they don't magically know what to do on their own. You use Amazon Route 53 DNS failover, which actively monitors the health of your endpoints. When it sees that your primary region is dead, it automatically routes your user traffic away from the unhealthy resources and directs it right to the backup region.
But traffic routing is totally useless if your data isn't there. Using AWS Backup, you can automatically copy your backups to multiple different AWS regions, ensuring your data is stored a minimum distance away from your production environment. And if your primary region relies on encrypted data, you can utilize AWS CAMS multi-region keys. These multi-region keys allow you to decrypt data newly encrypted in your backup region when the primary region is eventually restored. And you do it all without the latency of making cross-region API calls.
Section 4. The recovery testing trap. Don't just replicate.
Now, this leads us to a really deadly trap. Relying only on backups without recovery testing.
Teams will spend thousands of dollars replicating data, but they never actually test if they can restore it under pressure. Look, during a regional failure, you do not have time to guess. You can use AWS Backup to conduct scheduled restore testing to determine if you can meet your restore time objective. And if your application requires VMware Tools quiescence, you must validate that your backups meet your organization's needs by constantly testing your restores.
Because remember, without recovery testing, you do not have a business continuity plan. You have a wish.
Section 5. The Ultimate Resilience Mindset. Architect for Survival.
The ultimate resilience mindset is knowing we do not build systems under the assumption that the cloud is invincible. The cloud is made of concrete, fiber optic cables, and power lines, and eventually physical things break. We architect for survival. We isolate faults, protect our data, and route traffic dynamically. Which means when a region fails, immature teams panic. Mature teams, they just sit back, sip their coffee, and watch the traffic fail over.
Because in AWS, a disaster doesn't happen when a region goes offline. A disaster happens when you didn't plan for it. So ask yourself, if your primary AWS region went completely dark right now, would your business survive the night? Okay, let's dive right into this. Imagine for a moment your production systems are just completely destroyed. A nasty ransomware attack just encrypted your primary databases, and your entire network is totally paralyzed. You can practically feel the panic setting in across the company. But your lead engineer, they stay perfectly calm. They look at the team and confidently say, relax, just restore the backups. So they confidently open up the AWS console, completely ready to bring the business back online. But then their stomach drops. The backup vault is completely empty. Or even worse, the backup file is actually sitting right there, but when they run the restore operation, the database is completely corrupted. It absolutely will not mount. The disaster recovery plan just collapsed. Think about that for a second.
There's a saying in the industry, a backup that hasn't been tested isn't a backup, it's a wish. Relying on an untested backup strategy is exactly like jumping out of a burning airplane with a parachute you packed 5 years ago. You shoved it in a dark closet and you never once opened it to see if the canopy was actually still inside. You assume you are perfectly safe, right up until you pull the ripcord, and nothing happens. The impact? Catastrophic failure, massive downtime, and potentially millions of dollars in lost revenue.
All right, let's look at centralized AWS backup plans. Back in the day, we used to write these incredibly fragile manual scripts to trigger snapshots across every individual server. Well, in AWS, those days are over. Now we use AWS Backup. Think of it as a fully managed central command for your entire data protection strategy. It automatically creates snapshots, which are basically just point-in-time copies of your Amazon EBS volumes, your Amazon RDS databases, and your Amazon EFS file systems. And it stores them safely in a centralized backup vault. The best part? You don't do this manually. You build what are called backup plans. A backup plan is a fully automated policy where you define exactly how your systems are protected. You simply tell AWS Backup to find every single resource tagged as production, back it up every night at 2 a.m., keep those snapshots in warm storage for 30 days, and then automatically transition them over to low-cost cold storage for a year using lifecycle rules. It is completely hands-off.
Next up, defining RPO and RTO.
Now, we are getting into the two absolutely most critical concepts in disaster recovery. If you are taking your SOA-C02 exam, you absolutely must know these. I want to slow down slightly right here, because understanding the contrast between these two is absolutely vital. First, look at the left side. RPO, or Recovery Point Objective. It asks a brutal question. How much data are you willing to lose? If your backup policy only runs once every 24 hours, your RPO is 24 hours. So, if a catastrophic crash happens at hour 23, you just permanently lost a full day of customer transactions. Now, let's look at the other side, RTO, or Recovery Time Objective. This one asks, how long can the business afford to be offline during a crisis? If you have 50 terabytes of data sitting in cold storage, pulling that massive amount of data back into a live production database might literally take hours. That could completely blow past your allowed downtime, costing the business heavily.
Now here is where companies discover whether their backups actually work. What if a malicious actor completely compromises your AWS environment? They don't just stop at deleting your servers. Oh no, they go straight into your backup vaults and systematically delete every single snapshot. If you are relying on standard, unprotected backups, your entire company is gone. To survive this exact
terrifying scenario, you need immutable backups. AWS Backup Vault Lock enforces a write once, read many, or worm model on your storage. This is your ultimate safety net. Once you lock a vault in compliance mode and the grace period expires, those backups become completely immutable. Nobody can touch them, not your highest level administrators, not a compromised root user, and not even AWS themselves. No one can alter or delete those recovery points until their exact retention period is completely finished.
But locking the vault isn't enough. And listen closely, because this is exactly where people mess up. What if the data inside the snapshot was already corrupted before the backup even ran? What if your application requires a highly specific boot sequence that entirely fails when the server wakes up from a restored state? The crucial takeaway here is this. A successful backup job just means AWS successfully copied the underlying bits. It does not mean your application knows how to actually use those bits to get your business back online.
So, how do we solve that? Automated restore testing. This is exactly why AWS Backup includes restore testing. You absolutely do not wait for a massive ransomware attack to find out if your data is viable. Restore testing gives you an automated, periodic evaluation of your restore viability to mathematically prove you are actually meeting your RTO. Let's map out the exact sequence. You build a restore testing plan. It automatically pulls a recovery point, spins up the infrastructure in a completely isolated environment, and measures the exact time it takes to complete. You can even trigger an Amazon Event Bridge validation workflow to ping a health check endpoint on the restored server. This proves your data is uncorrupted and your application actually works. And the best part? Once the validation test finishes, AWS Backup automatically deletes all those temporary resources. You aren't paying a dime extra for them.
The absolute biggest trap engineering teams fall into is treating disaster recovery like a paperwork exercise. Their disaster recovery plans only exist on paper. They see the green success checkmarks on their daily backup jobs, they assume they are completely safe, and they go to sleep feeling secure. The backups existed, but the recovery plan was a lie. Think about that for a second.
Let's wrap up with the SysOps resilience mindset. This really summarizes the true operations engineer mindset. A backup is never truly a safety net until it has been successfully restored, validated, and measured under pressure. You design your policies, you lock your vaults, and you constantly test your parachute, because you never ever want your first restore attempt to be during a catastrophic failure at 3 a.m. So ask yourself, if your production systems went completely dark right now, are you absolutely confident your parachute would open?
Okay, let's dive into this. The engineering team is celebrating. They just deployed a beautiful, highly resilient architecture. They have an application load balancer distributing traffic across 3 different availability zones. Their auto-scaling groups are perfectly tuned to handle sudden traffic spikes. Their databases are synchronously replicated. They look at their dashboards, see everything glowing green, and think they are completely invincible. Then the entire AWS region goes dark. The load balancers stop responding. The databases vanish. The entire digital city just dropped off the map. They built redundancy, but they didn't build survival. Section 1. The operational trap: high availability versus disaster recovery. This is where people mess up. Multi-AZ is high availability. Availability zones are physically separated, isolated data centers within a single AWS region. If a localized flood or a power grid failure takes out one availability zone, your elastic load balancer seamlessly shifts traffic to the healthy instances in the other zones. But multi-AZ assumes the region itself is still alive. What happens when an unprecedented catastrophe takes out the entire region? Think about a massive ocean liner. Multi-AZ is having backup engines. If one engine explodes, the backup engine takes over and the ship keeps moving. The passengers don't even notice. But disaster recovery? That is the lifeboats. When the entire ship is actively sinking, having a redundant backup engine doesn't matter anymore. You need a way off the boat. To survive a regional failure, you must build across multiple AWS regions, choosing a disaster recovery strategy based on your budget and how much downtime your business can actually survive. Section 2. The Pilot Light strategy for disaster recovery. The first strategy is the Pilot Light. Think of this like the pilot light in a gas furnace. It's a tiny continuous flame. In AWS, this means you continuously replicate your core data, like your Amazon RDS databases and DynamoDB tables, to a secondary region. Your data is live and ready, but your web servers, your worker nodes, your expensive compute infrastructure, it is completely turned off. When the primary region dies, you trigger an automated script. turn on the gas. Provision the compute resources around your replicated data, and shift the traffic. The trade-off? You save a massive amount of money on compute costs, but the recovery takes time. You are accepting a longer recovery time objective. If you can't wait for servers to boot up, you use warm standby. In a warm standby strategy, your secondary region isn't just holding data, it has a scaled-down version of your full environment always running. It's live, but it's small. If the primary region fails, you don't have to build infrastructure from scratch. You just scale up the existing auto-scaling groups in the secondary region to handle the full production load. The trap here? Cost. You are continuously paying for compute capacity that you aren't fully using. Both Pilot Light and Warm Standby are examples of active/passive failover. Amazon Route 53 uses health checks to monitor your primary region. As long as it is healthy, 100% of your traffic goes there. The secondary region is purely passive, waiting in the shadows. But the second Route 53 detects that the primary region has failed, it triggers DNS failover and routes all your users to the backup region. But what if your business loses millions of dollars for every single minute of downtime? Think about that for a second. Section 3. Active/active failover for zero downtime. To get zero downtime, you build an active/active architecture. Both Region A and Region B are fully scaled, and Route 53 routes live customer traffic to both simultaneously. If one goes dark, traffic simply shifts to the other. But here is the massive real-world trap: operational complexity. Keeping distributed databases perfectly synchronized across the globe in real time without replication latency destroying the customer experience is a nightmare. Active/active is incredibly expensive and operationally exhausting. Section 4. The fatal testing flaw: untested runbooks. Teams will spend months building these cross-region failover environments, but they never actually test them. They rely on paper runbooks. Then, when the primary region actually fails, they trigger the failover, only to discover their database schemas are out of sync, their Route 53 health checks are misconfigured, and their Amazon machine images don't even exist in the secondary region. A disaster recovery plan that has never been tested isn't a plan. It is a massive operational blind spot. This is the SysOps resilience mindset. You do not assume the cloud is invincible. You do not assume that running in 3 availability zones means you can survive a disaster. High availability keeps you online during a glitch. Disaster recovery keeps your company alive during a catastrophe. Because in operations, the question isn't if the region will fail. The question is whether your lifeboats actually float when the ship starts going down. All right, let's dive right in. Today, we're going way beyond basic infrastructure. We are looking at the actual business path to resilience. Part 1, the partial outage nightmare. Picture this. You're staring at your dashboard. The CPU is hovering at a nice, comfortable 30%. Memory utilization, perfectly stable. Your primary Amazon Aurora database is responding to queries in under 2 milliseconds, and your Elastic load balancers are actively routing traffic. Everything on the screen is just glowing green. But your phone is absolutely blowing up. Customers are screaming on social media. Why? Because the checkout button is completely broken. Zero revenue has come in for the last 40 minutes. You're sitting there, totally confused. Your infrastructure is online, the database survived, the systems are technically alive, but the business is still dead. Yeah, that right there, that's the absolute nightmare of a partial outage. You see, in a modern distributed cloud environment, your application rarely just crashes in one massive catastrophic failure. It's usually more subtle than that. Instead, it trips over a hidden dependency. Let's say your primary checkout service needs to call this minor third-party API just to calculate a regional shipping tax. Well, suddenly, that minor API slows down. Notice I said slows down. It doesn't crash and give you a nice fast error. It just starts taking 15 seconds to respond, instead of its usual 15 milliseconds. Section 2. Cascading failures. Or as I like to call it, the airport analogy. Think about a massive international airport. If just a single baggage carousel breaks down, well, the bags pile up. And because the bags are backed up, the ground crews can't load the planes. Because the planes can't be loaded, they can't leave their gates. And because the gates are completely full, incoming flights have literally nowhere to park, so they just have to circle in the sky until they run out of fuel. One single broken belt just grounded every single flight in the city. And honestly, that is exactly how a cascading failure destroys your AWS environment. Your web instances are just sitting there waiting on that slow shipping API. And while I wait, the application keeps its database connections wide open. As more and more customers try to check out, more and more connections get held open in this frozen state. Within minutes, boom, your connection pool maxes out. Suddenly, your perfectly healthy database rejects all new queries from every other part of your application. The entire platform just collapses like a stack of dominoes. Part 3. The metric trap. Understanding infrastructure limits. Now, here is a crucial point. This is where operations teams realize a massive trap, both on the SOA-C02 exam and in real everyday production environments. The trap is relying solely on infrastructure metrics to trigger your automated responses. Think about it. When an application is deadlocked, just sitting there, helplessly waiting on a network call, it isn't actually doing any computational work. And because it's not working hard, its CPU utilization actually drops. Listen closely, because this is where people mess up. If you have an Amazon EC2 auto-scaling group configured to scale out based on high CPU, it is not going to launch a single new instance to help you out, not one. It looks at that low CPU and literally assumes your servers are just bored. Your metrics look absolutely perfect, precisely because your system is silently failing. So to actually survive this, you have to break that operational dependency chain. You need application-level visibility. You can't just ask an EC2 instance if its operating system is running. That's not enough. You have to ask the application itself if it can actually process a customer transaction. Section 4. Deep health checks as your Route 53 defense. Here's the cool thing. Amazon Route 53 doesn't just ping an IP address to see if a server is there. You can configure advanced health checks that make an actual HTTPS request to a specific custom endpoint on your application. Route 53 can read the response and perform specific string matching, literally scanning the page for a targeted phrase like transactions flowing or dependencies okay. So in practice, your developers write a deep health check script. This script actively verifies the database connection, tests that tricky shipping API, and if everything works, it writes that specific string. But if the shipping API freezes, the script fails, and the string disappears. The exact second that happens, Route 53 marks the endpoint as unhealthy. It doesn't matter that the EC2 instance is powered on. It doesn't matter that the Aurora database is running smoothly. Route 53 knows the business is failing. Part 5. Business continuity and failover routing. When you combine those deep health checks with Route 53 failover routing, you achieve real, actual business continuity. The moment that deep health check fails, Route 53 automatically stops sending your users straight into that traffic jam. It immediately reroutes incoming DNS queries away from the paralyzed architecture. Instead, it sends them over to a secondary healthy AWS region, or even just to a static Amazon S3 bucket displaying a graceful, "We'll be right back" maintenance page. Section 6. The resilience mindset. Making the operational shift. This whole approach? This is the operational resilience mindset. As a SysOps engineer, you really have to stop assuming that green infrastructure dashboards equal a working application. You have to proactively map out every single dependency bottleneck. You have to ensure developers are using timeouts and circuit breakers so a slow API doesn't completely exhaust your database. And you've got to configure DNS routing failures that actually protect the customer experience when the application layer degrades. Because at the end of the day, we do not monitor servers. We monitor the business. Think about that for a second. Because an architecture that keeps the servers perfectly healthy while the business completely dies is, quite simply, a failed architecture.
Picture this. Marketing just launched the absolute biggest campaign of the year. Traffic is surging to your platform and you're watching the metrics climb. But honestly, you aren't sweating it. Why? Because you built a highly resilient architecture. You've got an Amazon Elastic Load Balancer sitting cleanly in front of a massive Amazon EC2 auto-scaling group. The entire system is explicitly engineered to handle this exact massive traffic spike scenario. You're feeling pretty good.
But then, the visceral panic sets in. Out of nowhere, 504 gateway timeouts start appearing in your logs. You frantically refresh your dashboard and, one by one, your perfectly healthy servers simply vanish from the load balancer's target group. They're just gone. Total downtime. And every second they're down, your company is losing serious money.
Here is the terrifying 4-minute chronological timeline of total platform death. First, your initial targets fail under the immense load. Second, auto-scaling frantically tries to launch new instances, but they just aren't booting fast enough to catch up. Third, that massive wave of incoming traffic slams directly into your few surviving instances.
And fourth, their CPUs peg at 100%, they lock up, and they drop completely offline. Within 4 minutes, your platform is dead. You built a traffic control system to protect your infrastructure, but instead, the safety system itself just caused the outage. In this explainer, we're going to dig into exactly why that happens.
Section 1. How load balancers actually think.
If you're studying for your SOA-C02 exam, understanding the underlying mechanics of an elastic load balancer is absolutely crucial. At its core, an ELB is a system that accepts incoming client traffic and routes those requests to registered targets across one or more availability zones. Think of a load balancer exactly like a stadium security guard doing crowd control during a massive emergency. You've got thousands of people rushing the dates. The ELB is that guard, directing 10 people to door A and 10 people to door B. It's supposed to keep the flow moving evenly so no single door gets crushed.
But here's the crucial point. The security guard is only supposed to send people to open doors. Think about that for a second. The foundational rule of the ELB is that it must only route traffic to open, healthy targets. It constantly monitors the health of its registered targets to make sure this happens.
Section 2. The Target Health Track. Now this is exactly where people completely mess up, falling right into the target health trap when engineering teams configure bad health checks. Let's look at the difference. A shallow health check just pings port 80 to see if the EC2 instance is powered on. If it responds, the ELB thinks the target is healthy. But what if the application running inside that instance actually crashed 10 minutes ago? You've just created a false healthy target. The ELB is blindly throwing user traffic into a dead application's black hole. On the other hand, a deep health check verifies the application is actually running and responding correctly. This allows the ELB to accurately mark the instance as unhealthy and actually stop routing traffic to it.
Section 3. Auto-scaling bottlenecks. You might think using deep health checks keeps you safe, right? But doing things right introduces a completely hidden danger. Let's map out how this cascading failure actually happens. Step 1. Your deep health check accurately detects a dead app. Step 2. Auto-scaling terminates that unhealthy instance to launch a replacement. Step 3. And this is the absolute killer. There is an auto-scaling lag. It takes time for a new instance to boot, run its startup scripts, and pass its own health checks. And step 4, while you wait for those to boot, the ELB still has thousands of users hitting the front door. It dumps all that traffic onto your few remaining healthy instances, instantly overloading them.
And that leads to this really emotional realization. Because the remaining instances become overloaded, they've failed their health checks too. So the ELB removes them as well. The load balancer itself has become the bottleneck. The ELB systematically hunts down and destroys your fleet, failing instances one by one.
Section 4. Connection Draining Failures.
Now, assuming your fleet actually survives that initial spike, you still have to navigate scale-in events. Connection draining, which AWS also calls deregistration delay, is a mechanism meant to protect your users. When an instance is marked for termination, you don't want the ELB to just sever the connection immediately. That would drop a customer right in the middle of your checkout process, which means lost money. Instead, connection draining instructs the ELB to stop sending new requests, but wait for existing in-flight requests to complete before finally pulling the plug.
But here is the major failure mode. What happens if you have an application deadlock? Imagine a completely frozen database query. The ELB will politely hold those connections open, waiting for a response that is simply never coming. It ties up your resources indefinitely until the maximum timeout finally expires. Your safety feature just turned into a massive liability.
Section 5. Uneven Traffic Distribution.
This is the silent killer of regional architectures that catches almost everyone off guard. Imagine you have a network load balancer where cross-zone load balancing is disabled by default. Let's say you have 2 instances in availability zone A and 8 instances in availability zone B. Because cross-zone is disabled, the DNS routing strictly splits the incoming global traffic 50-50 between the 2 zones. That means those 2 poor servers in AZA are forced to handle 25% of the total global traffic each. They are getting completely crushed. Meanwhile, the 8 servers in AZB are sitting there doing almost nothing. Your dashboards are going to show you have plenty of overall capacity, but you'll be dropping requests because one zone is entirely overwhelmed.
The immediate fix for this: turn on cross-zone load balancing. This simple toggle ensures every single instance, regardless of which availability zone it sits in, carries the exact same weight. The load balancer nodes can then distribute traffic globally across all of your registered targets. Problem solved.
So what should you take away from this explainer? You need to adopt an operational resilience mindset. You cannot simply turn on autoscaling and assume you're magically protected. You must configure deep application-level health checks. You must match your connection draining timeouts to your actual workload reality. And you absolutely must explicitly design your cross-zone routing to prevent localized meltdowns.
I want to leave you with this final thought. A load balancer doesn't magically prevent failure. It redirects it. If your underlying instances aren't properly scaled and configured to handle that redirected load, the traffic control system doesn't save your production environment. It becomes the disaster. So I ask you, look at your architecture right now. Are your safety systems actually protecting your infrastructure? Or are they secretly setting the stage for your next massive
Okay, let's dive right into this. Welcome to today's Explainer, where we're going to tackle a scenario that absolutely strikes fear into the heart of every single cloud engineering team. Picture this. Your production environment is completely broken. Nobody knows why, and everyone is just completely baffled. So you jump onto the emergency bridge call, right? The tension is incredibly high. You look at your staging environment, and it's perfectly fine. The application code is identical, the deployment pipeline is glowing green, and every single engineer on the call is staring at their screens, insisting on this exact phrase: nothing changed. But, as we're about to see, that is almost never the actual truth. Because when you finally start digging past this high-level dashboards, you realize, well, actually, everything changed. Just look at this timeline. 3 months ago, an engineer manually tweaked an EC2 security group in the console during some minor incident, and they never wrote it down. 2 weeks ago, someone manually adjusted an elastic load balancer timeout to fix a sluggish response. 4 days ago, a developer modified a database parameter group by hand. Over time, production drifted so far apart from staging that literally nobody understood the environment anymore. The entire infrastructure just became completely unknowable. Section 1. What is configuration drift? Now, what's really interesting about this concept is, well, let's just read the definition right here. Configuration drift is the slow, quiet accumulation of undocumented manual changes that cause environments to become wildly inconsistent over time. You know, in AWS, human error isn't usually someone accidentally deleting a production database. Honestly, that's a loud error. The real danger is this exact slow, quiet accumulation of tiny tweaks that go completely unnoticed until everything breaks. To really visualize this, imagine a team of construction workers building 2 totally identical skyscrapers. But every single night, workers sneak into the production building and secretly change the blueprints. They move a support beam over here, they delete a fire suppression system over there. A year later, you don't have 2 identical buildings anymore. On the left, you have building 1. Safe, predictable, strictly follows the original blueprint. And on the right, you have building 2, an unpredictable trap. That emotional weight of a totally compromised foundation, that is exactly what happens to your cloud architecture. Which brings us to Section 2, the Snowflake server trap. This leads us directly into what operations teams call the Snowflake server trap. Look, when you have 2 servers, manually configuring them through a user interface, that's easy. But when you have 200 servers, manual changes scale terribly. You eventually end up with a uniquely fragile fleet where every single machine is just slightly different and totally impossible to replicate. And listen, this is where people mess up. This is a massive trap, especially if you're taking your AWS SOA-C02 exam. And it's the exact reason companies suffer catastrophic, prolonged outages. Let's walk through this sequence. Step 1. A server starts dropping connections at 3 a.m. Step 2. An on-call engineer panics, logs right into the AWS management console, and applies a manual fix, just clicking around until those red alarms turn green. Okay, the immediate fire is out. But then we hit Step 3. Autoscaling triggers later to handle a normal traffic spike. And Step 4. The new servers launch using the old configurations and they immediately fail. They basically just destroyed their infrastructure consistency just to put out a temporary fire. Suddenly, you're drowning in operational chaos. Half your fleet is running the correct original configuration that's used by your automated deployments, but the other half, it's running a ghost configuration, a setup that literally only exists in the memory of the engineer who clicked a button in the middle of the night. Think about that for a second. How can you reliably scale a massive business on ghost configurations? Simply put, you can't. Section 3. Infrastructure as Code. To stop all of this chaos, you have to fundamentally change how you interact with the cloud. You have to stop relying on human memory entirely and adopt an infrastructure as code mindset. So the crucial point here is recognizing this massive shift. The old way,
That was clicking buttons in the AWS Management Console. The new way is defining your entire architecture in simple text files. We no longer click buttons, we write code.
Let's look at exactly how AWS CloudFormation handles this. You write out your VPCs, your subnets, your auto-scaling rules, your alarms, all entirely in text files. And because it's code, it's version-controlled and it's peer-reviewed. When you execute these templates, AWS reads the code and provisions identical resources in a matter of minutes. This provides true repeatability. Let's say your primary AWS region completely fails. You don't spend 3 days scrambling, trying to remember what buttons you clicked 5 years ago. No, you just deploy your code in a new region and recover effortlessly.
Section 4. The Mature Automation Mindset.
Achieving that elite level of resilience requires adopting a true automation mindset where you treat your infrastructure exactly like your application code. Here's exactly how you enforce that standard in the real world. If an engineer wants to change a security group rule, they change the code and submit a pull request. You use automated pipelines for safe, consistent deployment across every single environment. But what if someone does try to go rogue and make a manual change in the console? Well, you deploy tools like AWS Config or AWS Systems Manager to instantly detect that drift and then automatically revert those manual changes right back to the intended state. That way, you always maintain total architectural control.
As a SysOps administrator, or frankly, anyone managing cloud environments, this quote on the screen is something you absolutely need to internalize. A manual change in production isn't a quick fix, it is a time bomb. If your infrastructure exists only in the memories of your engineers, you do not have a resilient system, you just have a disaster waiting to happen.
And that brings us to our golden rule for modern cloud engineering. Keep this memorable operational mantra in mind every single time you log in. The console is for looking, code is for building. If you stick to that, you'll tame configuration drift for good. So I'll leave you with this question to ask your team tomorrow morning. Are you building a truly resilient architecture, or are you just planting invisible time bombs? All right, let's dive right into it. Today, we're unpacking a concept we call the CloudFormation trap. And more importantly, we're going to figure out how you can safeguard your automated infrastructure.
Let's set the scene. We'll call this first part the Tuesday disaster.
Picture this. It's a completely normal Tuesday afternoon. An engineer pushes what looks like a routine infrastructure update. The pipeline runs, and the automated deployment begins.
At first, everything looks perfectly fine. But then, the Slack channels just start exploding. The load balancers are dropping traffic. The auto-scaling groups are terminating perfectly healthy instances. And the databases, they are literally vanishing right from the console. You jump on the incident bridge, and that cold realization hits everyone at the exact same time.
The automation system just turned against production. The infrastructure is deleting itself in real time.
So, how does this actually happen? Let's talk about the mechanics behind this. Think of it as the factory robot.
If you're using AWS, you know CloudFormation is the engine of your infrastructure as code. You write a template describing all the AWS resources you want, and CloudFormation provisions and configures them as a single cohesive stack. When you rely on it, you can predictably and repeatedly deploy your entire architecture across multiple environments. It's supposed to be flawless.
Think of CloudFormation like an enormous, highly efficient industrial factory robot. If you hand it a blueprint for a car, it builds a perfect car every single time. But here's the catch. The robot has zero common sense. If an engineer accidentally hands it a blueprint that is missing the engine, the robot isn't going to stop and ask if you're sure. No. It will ruthlessly tear the engine out of your existing car just to perfectly match those new instructions. Here's the process. When you update a stack, CloudFormation compares the new template against the previous configuration, actively looking for changes. If everything is valid, it applies the updates. Simple enough, right? But if the deployment hits an error, say a resource name already exists in the account and fails the pre-deployment validation, CloudFormation doesn't just leave your infrastructure sitting there half-finished. Instead, it triggers an automatic rollback. It attempts to reverse every single change to return the stack to the last known stable state. Which brings us to the real trap here, configuration drift. Now, here is where automation actually becomes more dangerous than manual changes. The rollback sequence assumes it has total, predictable control over the environment. But what if a stressed-out engineer made an emergency manual change to a security group 2 weeks ago directly through the console and just never updated the code? That right there, that is configuration drift. The physical reality of the cloud no longer matches your CloudFormation template. all because a single resource was modified outside of the automation. So, when the automatic rollback hits that undocumented manual change, it gets confused. It expects the old configuration but finds something completely different. And because of that, the rollback fails. Your stack is now completely paralyzed in an update rollback failed state. Think about that for a second. It can't deploy forward, it can't roll backward, and half of your production environment was already deleted before the original error even happened. To fix it, you have to perform a manual stack recovery. You're forced to blindly skip the broken resources just to unlock the stack status, all while your customers are completely offline and you're potentially losing money by the second. So, how do we stop this from happening? We need to build some serious stack guardrails.
A mature SysOps engineer doesn't let this happen. You have to catch the manual changes before the robot starts tearing things down, and you do that by using drift detection. Drift detection evaluates your stack and reports exactly which resources have been modified or deleted outside of CloudFormation. You run this before you deploy, so you aren't suddenly ambushed by an emergency fix from 3 weeks ago that ends up breaking your automated rollback.
But the ultimate defense against an automated disaster? That is a stack policy. Out of the box, CloudFormation just assumes it has permission to modify or delete anything inside its stack. A stack policy is a separate JSON document that explicitly protects your most critical resources. You can literally write a policy that says, I do not care what the new template says. Never, ever delete the production database. If you have that in place, even if an engineer accidentally deletes the database from the code or a rollback goes completely wrong, the stack policy intercepts the robot. It blocks the deletion, the database survives. This is the true infrastructure automation mindset. Automation is incredibly powerful, for sure. But without guardrails, it simply allows you to destroy your company at lightning speed. You have to assume human error will happen. You have to protect your critical resources with stack policies, and you have to constantly check for configuration drift. Because the only thing worse than a manual configuration mistake is an automated system perfectly executing the wrong instructions. So take a look at your own pipelines today and ask yourself, are your automation tools building your future, or are they just waiting to dismantle it?
Hey everyone, welcome to this explainer. Look, today we're going to take a sledgehammer to one of the absolute biggest bottlenecks in cloud engineering, the manual management of servers. We're talking about the end of SSH chaos, and we'll see exactly how mastering AWS Systems Manager changes, well, absolutely everything. Picture this. It's Friday night. A critical zero-day vulnerability just dropped. Your security team suddenly sends out a massive red alert. The message? Every single server in production needs to be patched by morning.
So you look at your architecture, and you realize you don't just have a handful of machines. You have exactly 500 Amazon EC2 instances running your backend. Your operations team immediately starts doing what they've always done, right? They open their terminals, they generate their SSH keys, they log into the first server, they download the patch, they install it, they reboot, then they log into the second server and realize they have 498 left to go.
They are exhausted. I mean, they are literally working overnight. And by server number 80, mistakes just start happening. Look, when you only have 5 servers, manual operations are annoying, sure, but they are doable. But when you have 500 servers, manual operations become completely impossible. People start skipping steps, updates get applied inconsistently, somebody accidentally forgets to exit a maintenance mode, fast forward a week, and half your fleet is running a totally different software version than the other half, and your applications just start failing randomly. This means downtime, it means lost revenue. This is what we call SSH chaos. You aren't really managing an architecture anymore, you're just running around putting out hundreds of tiny localized fires. The infrastructure has scaled completely beyond human control.
To actually survive at this scale, you have to undergo a total paradigm shift. You absolutely must stop thinking about individual servers and start thinking about fleet management. Think about an air traffic controller at a massive international airport. When a huge storm rolls in, they don't run out onto the tarmac with flashlights to physically guide every single airplane by hand. That would cause an absolute catastrophe. Instead, they sit in a secure, centralized command center. They look at a massive radar screen, and they broadcast automated, synchronized instructions to hundreds of pilots simultaneously. Well, in AWS, your central command center is AWS Systems Manager. Systems Manager is literally the core service for operational automation. It allows you to centrally view, manage, and operate thousands of nodes across your entire AWS environment. Heck, even your on-premises data centers.
But to actually take control of that massive fleet, you need its most powerful tool, and that is Run Command.
Run Command is incredible because it lets you execute scripts on thousands of instances simultaneously without ever opening an SSH connection or logging into a Bastion host. Instead of connecting manually, you just send an instruction to the Systems Manager agent. Now, this is a lightweight piece of software running invisibly in the background of your instances. You just say, hey, update the web server daemon, and you target those instances using their AWS tags. Boom! Within seconds, 1,000 web servers receive the instruction and update themselves all at once. You just get to sit back and watch the success codes roll in.
Now, here is where manual operations completely collapse. And pay attention, because this is where people really mess up. The absolute deadliest trap engineering teams fall into, both in real-world outages and on your AWS SysOps exam, is treating patches like a manual chore. If you rely on humans to remember to patch servers, you will inevitably end up with missed security patches. Think about it. An engineer goes on vacation, a maintenance window accidentally gets skipped, and suddenly you've got a highly vulnerable server sitting completely exposed in production, just waiting to be compromised.
It all really comes down to this core truth. Scaling operational complexity by throwing more human beings at the problem never works.
And this is exactly why mature teams use AWS Systems Manager Patch Manager. Patch Manager doesn't just install updates. It completely automates your entire fleet's compliance. You define what's called a patch baseline. This establishes exactly which types of patches are approved, like, say, critical security updates, and how many days the system should actually wait before installing them. You then simply link this baseline to a Systems Manager maintenance window.
So then, at 2 a.m. on a Sunday, Patch Manager just wakes up. It scans your entire fleet, it identifies the missing updates, it installs them, and then it reboots the servers gracefully. Nobody had to log in, nobody lost sleep. Automation didn't just save time here, it completely removed human error from the equation. But true fleet management goes way beyond just installing software. I mean, what if an entire database cluster needs to be safely taken offline, backed up, and restarted in a highly specific sequence? You definitely don't want to rely on some outdated text runbook stored in a random wiki, hoping a stressed, sleep-deprived engineer doesn't misread it at 3 in the morning. Instead, you use Systems Manager automation documents. An automation document is a predefined code-based workflow. It essentially turns a massive, complex operational procedure into a single automated execution. Every single step is strictly defined in code. So if a disk fills up or an application freezes, an Event Bridge alarm can automatically trigger that document to safely remediate the issue, step by step. Zero human intervention. The system just heals itself.
This is how operational consistency actually returns to your environment. When you automate everything, your servers stop acting like fragile, unpredictable snowflakes. Every single deployment is identical. Every security patch is guaranteed. The SSH chaos completely disappears because you physically lock down the inbound ports on your security groups. I mean, you don't even need them anymore. And this really brings us to the ultimate SysOps automation mindset. We do not automate just to save time. We automate because humans are terrible at doing the exact same thing 500 times in a row without making a mistake. As an AWS SysOps administrator, your goal isn't to be the fastest engineer at logging into a broken server.
Your goal is to build an operational automation system so powerful that you never have to log into a server again. So I want you to look at your own architecture today. Are you still running out onto the tarmac with a flashlight, or are you ready to become a true commander of your fleet?
All right, let's dive right into this explainer. Picture this scenario. Your dashboards are flashing red color. Traffic just exploded out of nowhere. The CPU on your web servers pegged at 100%. And your requests are timing out left and right. Customers are flooding support, completely unable to load the app. But hey, you aren't panicking yet, right? Because you built an Amazon EC2 auto-scaling group, the system is supposed to save you. So you watch the console, waiting for those new instances to launch and absorb the load. But they don't. Or, well, they do, but it's way too late. The infrastructure reacted, sure, but just not fast enough. So why did your auto-scaling group just fail you? This right here is the auto-scaling lie that nobody really talks about. There's this dangerous illusion in the cloud computing world that auto-scaling will instantly save your systems from sudden traffic spikes. But in reality, standard dynamic scaling is entirely reactive. It monitors your CloudWatch metrics, sees that your servers are actively dying, and only then decides to add capacity. Think about that for a second. Your servers literally have to be failing before the system even tries to step in and help. Which brings us to the fire department delay and the reality of reactive scaling. Think about a city fire department. If you wait until a building is completely engulfed in flames to pick up the phone and call for help, sure, the firefighters are going to dispatch immediately, but they still have to drive across town. They have to unroll the hoses. They have to connect to the hydrant. By the time the water actually hits the fire, the roof has already caved in. And that drive across town? That is your scaling delay. Here is the brutal physical reality. When an auto-scaling policy triggers, AWS doesn't just magically manifest a fully functioning web server in a single millisecond. It has to physically provision the underlying EC2 instance. Then, it boots the operating system. Next, it runs your custom user data scripts. And finally, it has to wait for the instance to pass its health checks. Look, if your application takes 4 minutes to initialize, your customers are experiencing 4 minutes of total downtime. That is real failure, and that means real money lost. And here is exactly where the problem compounds. 300 seconds. Let's say your new instances finally boot up, but the traffic is still climbing. You desperately need more servers, but your auto-scaling group doesn't launch them. Why? Because of cooldown periods. A scaling cooldown is a built-in pause designed to let your newly launched instances stabilize before the system makes another scaling decision. If your simple scaling policy uses the default cooldown of 300 seconds, AWS literally sits on its hands for 5 agonizing minutes, completely ignoring the alarms while your remaining servers just melt down.
So the crucial question here is, how do SysOps engineers actually survive these bottlenecks? Enter target tracking, or what I like to call the thermostat approach. To keep systems alive, professionals abandon those rigid, simple scaling rules and adopt fluid policies instead.
Let's compare the two. We have simple scaling, which is incredibly rigid and reactive. And we compare that to target tracking, which is fluid and much more thermostat-like. Think of target tracking exactly like the thermostat in your house. Instead of telling AWS, hey, add exactly 2 instances if the CPU hits 90%, you tell AWS, keep my average CPU utilization at exactly 50%. AWS then automatically creates and manages all the alarms, calculating exactly how many instances to add or remove to maintain that perfect optimal temperature. It fluidly scales your capacity in direct proportion to the actual load on your application.
But wait, what about cyclical workloads? There's a hidden flaw here, and honestly, this is exactly where people mess up. Even target tracking is still reacting to what has already happened in the past. If you have a cyclical workload, let's say your traffic reliably spikes every single morning at 9 a.m. when the East Coast logs into work, reactive scaling is always going to put you behind the curve. Your servers are still going to choke at exactly 9:01 a.m. while auto-scaling scrambles to catch up to that morning rush. To truly beat the traffic, you need an infrastructure that basically knows the future. So let's talk about predicting the future, where machine learning meets infrastructure. This is where predictive scaling enters the picture and completely changes the game. Predictive scaling changes absolutely everything. It uses machine learning to analyze up to 14 days of your historical load data. It identifies your specific daily and weekly traffic patterns to forecast your future capacity needs, and then proactively provisions that capacity before the traffic even arrives. So, at 8:45 a.m., predictive scaling just goes ahead and adds the capacity. The instances boot up, the application warms up, so when that 9 a.m. traffic tsunami hits, your infrastructure doesn't even flinch, because the servers are already right there, waiting for the users. But hang on, what if traffic spikes unpredictably? Think about a sudden viral marketing campaign, or a massive, completely unexpected news event. If you rely solely on predictive scaling, you are looking at catastrophic failure. The machine learning model only knows your past. It has no idea that an influencer just tweeted your link to 10 million people. And this brings us to the ultimate SysOps operational mindset, which is a layered scaling architecture. Real production architectures do not rely on just one scaling method. They use both. You use predictive scaling to handle your anticipated baseline load, the traffic you know is coming. And then you layer target tracking dynamic scaling right on top of it to react to those unexpected sudden surges that nobody saw coming. This way, you cover the expected and you cover the unknown. Which leads us to a pretty harsh operational truth. An infrastructure that scales too late is an infrastructure that still went down. As an engineer, you have to understand that autoscaling is a tool. It is not some invincible shield. It is permanently bound by the laws of physics, software initialization times, and the configuration limits that you set. So what is your key takeaway from this explainer? Stop relying purely on reaction. Ask yourself, Is your infrastructure waiting for the fire to start before it calls for help?
Welcome to this explainer on the immutable architecture, the art of self-healing infrastructure. Let's just picture this scenario for a second. A critical production server just failed, right in the middle of the day. The CPU suddenly pegs to 100%, memory utilization skyrockets out of absolutely nowhere, and the main application process just completely locks up.
I mean, we've all been there, right? So the lead operations engineer cracks their knuckles, opens up their terminal, and prepares to SSH directly into the machine. They're getting ready for that grueling manual labor of tailing the error logs, restarting the core service, and painstakingly nursing that dying server back to health, step by step.
But here's where it gets interesting. Just as their fingers hit the keyboard, before they can even type a single command to diagnose the issue, the infrastructure automatically terminates the instance.
It just kills it. And less than a minute later, without a single human intervention, a brand new, perfectly healthy replacement server launches instantly and starts taking production traffic. The engineering team, they just sit there and stare at the screen. Nobody touched a keyboard, nobody issued a restart command. The system just handled it.
And this brilliantly illustrates what just happened. The infrastructure actually healed itself. Notice the contrast here. For decades, the traditional server management mindset treated infrastructure like a collection of pets. When a server got sick, you logged in, applied a manual hotfix, patched it, and stayed up all night trying to keep it alive. But those manual repairs, they create a massive, hidden danger, and that's configuration drift. If you fix server A by manually changing a file, but you forget to change server B, well, you suddenly have wildly inconsistent server configurations across your fleet. Your environment quickly becomes this fragile, unpredictable mess that nobody on the team truly understands. So that old mindset of repairing servers manually, it's dying. Welcome to immutable infrastructure. The absolute crucial point of this entire philosophy is this. In an immutable architecture, once a server is deployed, it is never modified, ever. If it breaks, if it gets hacked, or if it simply needs a basic software update, you do not try to fix it. You destroy it entirely, and you replace it with a perfect clone.
Think about this through a concept from nature for a second. Take biological cell regeneration. Your body doesn't try to surgically repair a single damaged skin cell. That would be wildly inefficient and, frankly, practically impossible. Instead, it simply sheds the dead cell entirely and generates a brand new one from its core DNA, replacing the damaged cell instantly and flawlessly. Now, over in AWS, your core DNA is the Amazon Machine Image, or AMI. An AMI serves as the fundamental building block and the basic configuration template for your instances. It's an exact, frozen snapshot of your operating system, your application code, and all of your necessary dependencies. It is your ultimate baseline, acting just like biological DNA.
But an AMI alone doesn't actually build a server. Just having the DNA isn't quite enough. That DNA needs very specific instructions on exactly how to run.
And this is exactly where Amazon EC2 launch templates come into play. A launch template defines the exact hardware configuration that's compatible with your AMI. It dictates the instance type, carefully specifying the compute power. It dictates the security groups, controlling what traffic is allowed in and out. It specifies the network subnets, deciding exactly where the server lives. And it assigns the IAM roles that the instance will use to access other services when it finally wakes up.
Now, here's the infrastructure mindset shift that most engineers honestly never realize. There is a massive trap on your SOA-C02 exam. And honestly, the exact reason so many companies suffer catastrophic extended outages is failing to understand launch template consistency. This is what we call the configuration drift trap.
Let's look at exactly how this happens. Let's say an engineer logs into an unhealthy instance and manually updates the application code to fix a really nasty bug. The server stabilizes, the memory drops back to normal. The engineer thinks they just saved the day, but they just created a time bomb. Because they repaired the server manually in the heat of the moment, they never updated the underlying AMI or the launch template. The blueprints are completely out of date. So the next day, traffic suddenly spikes. Your auto-scaling group detects the heavy load and immediately triggers automated provisioning to add more capacity. But here's the catch. Auto-scaling doesn't know anything about that engineer's manual hotfix. It rapidly reads the old launch template, boots up 5 new instances using the old broken AMI, and aggressively dumps live production traffic right onto them. And those new instances instantly fail.
You tried to repair the infrastructure instead of replacing it, and it brought down your entire business. To build true, self-healing systems that prevent this entirely, you absolutely must bind your launch template directly to an auto-scaling group. The auto-scaling group acts as your automated system administrator. It constantly monitors your EC2 health and reachability checks. The exact moment an instance fails a health check, the auto-scaling group mercilessly marks it as unhealthy. It shows absolutely no attachment to the server whatsoever.
It doesn't page you at 2 in the morning to ask for permission. It immediately terminates the bad instance, reliably reads your up-to-date launch template, and provisions a brand new, pristine instance to flawlessly maintain your desired capacity.
This is the disposable infrastructure mindset. Servers are no longer permanent, sacred fixtures that require constant feeding and care. They are entirely disposable units of compute capacity. By ruthlessly replacing versus repairing your infrastructure, you guarantee absolute operational consistency. Every single server in your entire fleet is an identical, perfect clone of your launch template. There are no snowflakes. There is zero configuration drift anywhere in the system. So as an AWS SysOps Administrator, you really have to look at the bigger picture and fundamentally shift your operational philosophy. You have to stop looking at individual servers as the end goal. Like the saying goes, you are no longer a mechanic whose job is to fix broken servers. You are an architect designing an ecosystem. You build the template, you define the automated health checks, you set the baseline that allows the entire system to manage itself.
And when a server inevitably dies under the massive weight of production traffic, you don't panic. You don't frantically open your terminal to start typing commands. You just sit back and watch the infrastructure rebuild itself. So think about your own environments for a second. Are you still exhausted from nursing 6 servers back to health in the middle of the night? Or are you ready to finally let your infrastructure heal itself?
Okay, picture this. Your deployment pipeline is glowing perfectly green. It's 2 p.m. on a Tuesday, and your developers, they are literally celebrating in the Slack channel. So the operations team goes ahead and shifts the traffic, and then immediately, the entire system collapses. I mean, database locks just absolutely skyrocket. You're watching your latency jump from a normal 50 milliseconds to a brutal 8 seconds. Customer transactions, they're completely failing. And the engineers are just frozen, right? Staring at their screens in total panic. They simply don't understand how this is happening. After all, the code was tested, the deployment was supposedly successful. But here's the harsh reality. The pipeline said success, while production was actively dying. Think about that for a second.
Section 1. The automation trap in CI/CD nightmares.
So this right here is the ultimate nightmare of modern CI/CD automation. Now, we all know continuous integration and continuous delivery are designed to remove that slow, manual toil of pushing code. Services like AWS Code Pipeline, they orchestrate the whole shebang, pulling source code, building it, running automated tests, and deploying it straight to your Amazon EC2 instances or containers. But you know, there's a dark side to all this automation. Automation doesn't just make good things happen faster. It actually allows you to deploy bad code at machine speed. Deploying software to a live cloud environment is exactly like switching railroad tracks while a massive freight train is moving at full speed. If that new track isn't perfectly aligned, it honestly doesn't matter how shiny the steel is. That train is going to derail.
And this leads us to a massive trap that engineering teams fall into all the time, both out in the real world and on your SOA-C02 exam. It's this dangerous assumption that just because code passed in staging, it's somehow perfectly safe for production. Listen, staging is a lie.
Think about it. Staging doesn't have millions of live users hammering the system. It doesn't have your massive production database, and it definitely doesn't have those unpredictable, totally chaotic traffic spikes of the real world. Because of this, hidden production-only failures will always slip through your pipeline. Now here is exactly where successful deployments become the most dangerous. If your operations team is just relying on a basic pipeline that pushes code to the servers and then instantly declares victory, well, they are flying completely blind. They're assuming the deployment worked just because the servers didn't crash. But we have to slow down and remember this crucial difference. Healthy infrastructure does not mean a healthy application. An EC2 instance might be running perfectly fine, humming along, while the actual code inside it is returning 500-level HTTP errors to every single customer.
Section 2. Deep Deployment Monitoring and Watching Business Metrics.
So how do we survive this? You absolutely need deep deployment monitoring. You can't just watch the pipeline.
you have to watch the real business metrics. You need to configure Amazon CloudWatch alarms to specifically monitor your application's error rates, request latencies, and your database connection pools from the exact second that new code goes live. Why? Because when that new code inevitably breaks something, you cannot rely on human reaction time. Imagine a deployment causes an outage, and an engineer has to manually log in, find the previous commit hash, build a whole new artifact, and then wait 15 agonizing minutes for a manual revert to process. Your business is bleeding money the entire time. That rollback delay is deadly.
This is why you need automated rollback strategies. Over in AWS, you can actually configure your deployment groups to automatically roll back the absolute instant a CloudWatch alarm enters the alarm state. The moment your error rate crosses your defined threshold, boom, the deployment system stops pushing the bad code and immediately reverts those instances back to the last known good revision. The system literally fixes the bleeding before the on-call engineer even gets paged.
But we can go even further than that. If you are doing what we call an in-place deployment, where you actually take down your active servers to install the new code, you are taking on a massive operational risk. Because if that rollback fails for any reason, your instances are left in a corrupted, half-deployed state.
Section 3. Blue/green deployments and reducing your blast radius. To truly reduce your deployment blast radius, mature operations teams use what are called blue/green deployments. It's a real game changer. In a blue/green deployment, you never, ever touch your live production environment. That is your blue environment, and it is actively serving your customers. Instead, your pipeline provisions a completely separate, identical infrastructure. We call this the green environment. It deploys the new code there, it runs validation tests there, and the best part? If green is totally broken, nobody cares. Your customers never even saw it.
But let's say green looks healthy. Well, you still don't guess. Instead, you shift just a small percentage of your production traffic over to that green environment. You closely watch those CloudWatch alarms we just talked about. And if the alarms stay quiet, then you execute the full blue/green cutover and shift the rest of the traffic.
And here is the real magic of this strategy. If that green environment suddenly collapses under the full production load, your rollback takes less than a second. Seriously, sub-second. You don't have to uninstall any code, you don't wait for servers to reboot, you just flip your Route 53 DNS record or your Elastic Load Balancer target group right back to the blue environment.
Section 4. The SysOps Mindset. Trust nothing.
Because remember, those old servers are still sitting right there, perfectly healthy, completely ready to take the traffic back. This is exactly the operational deployment mindset required for the SysOps exam. We do not trust deployments. We do not trust staging environments. We assume that every single line of new code is a direct threat to production stability. As an AWS operations engineer, your job isn't just to make sure the pipeline runs fast. No, your job is to build an environment that is so strictly monitored and a rollback system so resilient that you never have to fear a deployment again.
Because at the end of the day, in cloud operations, a successful deployment isn't defined by a green checkmark in a pipeline. It's defined by the fact that your customers never even noticed it happened.
Welcome back to The Explainer. Okay, let's just dive right into this because today we're looking at something that literally keeps cloud engineers awake at night. I want you to imagine a scenario for a second. It's late, you're staring at your monitoring tools, and then suddenly everything goes red. Your dashboards are just lighting up with failed SSH login attempts. We're talking thousands of them every single second. Security alerts are exploding across all your incident response channels. You jump onto the emergency bridge, your heart is absolutely pounding, and you're frantically trying to figure out how a fleet of internal back-end servers is suddenly reachable by automated botnets in Russia, China, and, well, pretty much anywhere else in the world. The panic is absolute. Section 1, The Ultimate Cloud Nightmare, How One Tiny Rule Exposed Everything. Section 2, The 0.0.0.0/0 Trap, or as I like to call it, the misconfiguration hackers love most. So to actually understand how we get caught in this trap, we have to look back at that emergency bridge. Somebody looks at the Amazon VPC configuration and they just go completely pale. Why? Because they realize this massive disaster wasn't some highly sophisticated state-sponsored hack. It wasn't a zero-day exploit. No, it was a temporary networking change made by a junior engineer who was just trying to troubleshoot a deployment issue 3 days ago.
You see, when you expose your infrastructure to the public internet, you aren't just inviting legitimate traffic. You are putting your servers on a global radar that is constantly, relentlessly being scanned. The exact second a server comes online with the public IP, it gets probed. And this is exactly why Amazon EC2 security groups are so incredibly vital. A security group is basically your instance-level firewall. It controls what traffic is allowed to enter, which is your ingress, and what traffic is allowed to leave, which is your egress. So picture this. An engineer is trying to fix a connectivity issue. They can't figure out why they can't SSH or RDP into a specific instance. Out of pure frustration, they edit the inbound rules of their security group, they select port 22, and they set the source to 0.0.0.0/0. They think they just fixed their broken connection, but what they actually did was accidentally authorize unrestricted SSH access to the entire planet. Let's visualize this for a second. Think about a massive, high-security skyscraper. Using an overly permissive 0000 rule to fix a connection issue is like removing the vault door in the basement during maintenance, propping all the lobby doors wide open, and then simply forgetting to reinstall the locks when you go home. Sure, the maintenance worker can get in easier now, but so can absolutely everybody else. Think about that for a second.
Section 3, Security Groups versus NACLs, the second layer of defense. Now, security groups are really only half the battle here. If a security group is the lock on a specific server's door, a network ACL is the security checkpoint at the entrance to the specific subnet neighborhood. Network ACLs operate at the subnet level to control inbound and outbound traffic. And honestly, this sets up a terrifying misconception that a lot of engineers have about how these two tools actually interact with each other. Let's slow down here for a minute because this concept is absolutely critical to understand. A lot of times, engineers do not understand the difference between stateful and stateless firewalls, and they end up creating massive security holes while just trying to fix broken applications. So security groups are stateful. This means if a security group allows an incoming request from the internet, it automatically allows the response traffic to flow back out to the user, completely regardless of your outbound rules. Network ACLs, on the other hand, are stateless. If you allow traffic in, the NACL will drop the response unless you explicitly write a rule to allow that return traffic back out. And this is exactly where people mess up. Just look at this cascading operational sequence. It's so common. An engineer tests the connection. They see the traffic drop. Because they don't explicitly realize the NACL is stateless, they assume the security group is broken. So what happens? The engineer mistakenly opens their security group to the entire internet, when the real problem the whole time was just a missing outbound NACL rule. This one fundamental misunderstanding creates a massive cascading security failure.
Section 4. Architecting least privilege. Dividing public versus private infrastructure. Relying entirely on a security group to protect a database that's just sitting in a public subnet is a massive architectural flaw. Proper layered network security means combining these tools intelligently and properly dividing your public and private infrastructure. So the really crucial point here is how we actually execute this. Step 1, place the database in a private subnet. Listen, if a server doesn't need to be spoken to directly by the internet, it should never be in a public subnet, period. Step 2, put it behind an application load balancer or a NAT gateway. And step 3, configure the database security group to specifically only accept inbound traffic from the exact security group ID of your web servers. When you place a database in a private subnet, you don't use IP addresses in your security group rules. By referencing the security group directly, you ensure that only your web instances can ever connect to the database on port 3306, and that automatically blocks everything else.
This perfectly illustrates the core philosophy of least privilege operations. You do not start by allowing everything and then trying to play whack-a-mole blocking the bad actors. It is a strict best practice to authorize only the highly specific IP ranges and resources that actually need access. You avoid large open port ranges. You systematically close doors, board up windows, and remove the exact pathways that ransomware and automated bots use to traverse through a network. A mature SysOps administrator understands that networking in AWS isn't just about making sure systems can communicate. It's about ensuring they actively cannot communicate with anything else.
Section 5. Convenience versus security, the enemy of cloud operations. We definitely have to have some empathy here, though. Overly permissive rules almost always happen because engineers are tired, they're under intense pressure, and they really just want the application to work so they can finally get some sleep. But in cloud operations, convenience is the enemy of security. An architecture that is perfectly functional but completely open to the world is not a successful deployment. It is a disaster waiting to happen. Which leaves us with this final question. Are you leaving your digital doors unlocked just to get to sleep faster?
Because in AWS, if you leave a door unlocked just to make your job a little easier tonight, a hacker will eventually walk right through it tomorrow. Make sure your architecture is properly secured, and I hope this explainer helps you lock down those doors for good.
Silent Sentinels, automated threat detection and remediation in AWS.
Your dashboards are completely green. The CPU utilization is normal, but right now, someone you don't know is quietly exploring your AWS infrastructure.
Part 1. The Silent Compromise. Compromised IAM keys and silent reconnaissance. They logged in using a compromised IAM access key. They are casually listing your Amazon S3 buckets, describing your EC2 instances, and quietly mapping out your network subnets. And your operations team has absolutely no idea. Everyone thinks production is fine. The attackers are already inside. You see, in the cloud, a breach isn't always a dramatic explosion where your servers get deleted. Often, it's a silent, creeping compromise. They slip through the front door and just watch. To catch them, you need a system that records every single action. Think about a high-end casino. The security isn't just the guards standing at the doors. There is a massive, invisible network of security cameras hidden in the ceiling, watching every single table, recording every hand dealt and every chip moved.
In AWS, that camera network is AWS CloudTrail. CloudTrail provides a continuous history of both API and non-API account activity made through the AWS Management Console, SDKs, and command line tools. Every time anyone does anything in your AWS account, creates a user, modifies a security group, or assumes a role, CloudTrail writes a log event.
It records exactly who made the request, the IP address they came from, the exact timestamp, and the user agent. It is the ultimate source of API visibility. If an attacker uses compromised IAM credentials to attempt a privilege escalation or suddenly queries your infrastructure from a strange location, CloudTrail captures their invisible fingerprints.
Now here's the terrifying part most companies never realize. Having the security footage doesn't matter if nobody's actually watching the tapes.
Your account generates millions of CloudTrail events a day. You cannot manually read through massive JSON files to find the one unusual login location or the one weird API call. You need an automated detective.
Part 2. Automated Detective. Amazon Guard Duty.
This is where Amazon Guard Duty comes in. Guard Duty is an intelligent threat detection service that continuously monitors your AWS environment. It doesn't just ingest your CloudTrail management events, it also analyzes your VPC flow logs and DNS logs to detect potential threats across your accounts and workloads. It uses machine learning and threat intelligence feeds to identify suspicious behavior. If an IAM credential is suddenly used from an IP address in a country you don't operate in, or an EC2 instance starts querying a known cryptocurrency mining pool, Guard Duty immediately flags it as a threat. It actively looks for reconnaissance activity, instance compromise, and account compromise.
But as your architecture grows, you run into another massive operational trap. How do you handle decentralized panic?
Imagine you have Guard Duty findings firing in one region, AWS config rule violations firing in another, and Amazon Inspector vulnerability alerts buried in a different dashboard. An attacker is moving laterally across your infrastructure, but your security alerts are scattered everywhere. You completely lack centralized visibility.
Part 3. Single pane of glass. AWS Security Hub.
To solve this, you need a single pane of glass. Enter AWS Security Hub. Security Hub gives you a comprehensive, centralized view of your security posture. It ingests the findings from Guard Duty, Inspector, Macy, and even third-party products into one unified dashboard. Instead of chasing alerts across 10 different services, your operations team opens Security Hub and instantly sees a prioritized list of security findings. Part 4. Automated Remediation, SOA-C02 exam and production environments.
On your SOA-C02 exam and in real production environments, operational security monitoring isn't just about looking at a dashboard. It's about building automated remediation. Here's how it works. When Security Hub aggregates a critical Guard Duty finding, like a compromised IAM key, it can route that event directly to Amazon EventBridge. EventBridge catches the event in milliseconds and automatically triggers an AWS Systems Manager automation runbook. That runbook executes a script that instantly revokes the compromised IAM access key and isolates the infected EC2 instance by changing its security group.
The threat is neutralized before the human on-call engineer even wakes up.
Part 5. Mature Detection Mindset. Relentless Automated Threat Detection.
This is the mature detection mindset. You must assume that attackers will eventually get their hands on a credential. You must assume your perimeter will be breached. As an AWS SysOps administrator, your job is to build an environment with so much operational visibility and such relentless automated threat detection that an attacker cannot take a single breath inside your account without setting off the alarms. Because the most dangerous threat in the cloud isn't the attacker who breaks in and breaks things.
It's the attacker who breaks in and just quietly watches.
All right, let's dive into continuous compliance and drift governance in AWS Config. Picture this. The auditors are finally here. Now, the executives, they aren't worried at all. When the infrastructure was built 3 years ago, they hired expensive consultants to make sure everything was perfectly secure and compliant. So they just tell the lead cloud engineer to export the standard reports and hand them over. But when the engineering team actually looks at the live production environment,
Cold panic spreads through the room.
Amazon S3 buckets holding sensitive customer data have been made completely public. Database encryption was quietly disabled during a late-night troubleshooting session 6 months ago. Half the EC2 fleet is missing required security tags. And unauthorized ports are wide open to the internet. Everyone thought everything was fine, but the infrastructure had been silently drifting out of compliance for years and nobody noticed.
And you know, this is the exact reason why audits fail. An environment is literally never static. Your engineers are constantly deploying new code, modifying security groups, and creating new resources just to keep the business running. If you don't have strict oversight monitoring those unmanaged changes, your infrastructure will inevitably drift. A perfectly secure architecture on day 1 can become a massive security drift nightmare by day 100.
Think about a rigorous health inspection in a busy restaurant. You can't just leave raw meat sitting on the counter for 3 weeks and then frantically bleach the kitchen the night before the inspector arrives. You still fail. The inspector doesn't just want to know if the kitchen is clean today. They want to know if it was clean every single day the business was operating, because if it wasn't, people already got sick.
So in AWS, you cannot rely on manual checks or point-in-time audits. You need a system that acts as an always-on security camera for your infrastructure. You need AWS Config.
AWS Config continuously monitors and records your AWS resource configurations. Every single time an engineer changes a security group, modifies an IAM policy, or launches a new server, Config writes it down. It creates an immutable configuration history. If a massive breach happens, you don't have to guess what your environment looked like 3 months ago. Config gives you the exact minute-by-minute timeline of who changed what.
But listen, simply recording changes is not enough to survive in production. You have to enforce governance. With AWS Config, you deploy compliance rules. You tell the system exactly what healthy looks like for your organization. You can deploy a managed rule stating that every single Amazon EBS volume must be encrypted, or maybe a custom rule demanding that no Amazon RDS database can ever be publicly accessible. Config constantly evaluates your live infrastructure against those exact rules.
Now here's the terrifying part most companies never realize.
During a real audit, auditors demand proof of continuous compliance. Think about that for a second. If a developer accidentally makes a database public and another developer notices and manually fixes it 2 days later, you still had a massive policy violation event for 48 hours. If you are missing governance controls, you have absolutely no record of that exposure. You are completely blind to the fact that customer data was sitting on the public internet for 2 days.
But when you use config, the moment that developer makes the database public, drift detection immediately triggers. The resource is flagged as non-compliant right there on your dashboard.
Now, as a SysOps administrator, you don't want to just stare at a red dashboard and manually fix things. You use remediation workflows. You can link an AWS config rule directly to an AWS Systems Manager automation document. The exact millisecond the database is made public, config detects the violation, flags it, and automatically executes the runbook to revoke the public access instantly. The database is secured before the developer even realizes they made a mistake.
And more importantly, Config provides comprehensive remediation tracking. It gives you the cryptographic proof you absolutely need to show the auditors exactly when the vulnerability appeared and exactly when the automation fixed it.
This is the operational governance mindset required for your SOA-C02 exam. Honestly, this is where people mess up. Amateur teams treat compliance as a massive, stressful paperwork exercise. They scramble once a year, manually checking servers, desperately hoping they don't find anything catastrophic.
Mature cloud operations teams, on the other hand, understand that human beings will always make mistakes. They build continuous compliance monitoring directly into the fabric of the account.
Because in a modern cloud architecture, an audit shouldn't be a terrifying discovery of everything that went wrong. It should just be a printed receipt proving that your automation did its job.
Welcome to This Explainer. Today, we're diving into the illusion of security, and we're going to look at exactly how to master AWS encryption and KMS operations. Pause 1.0 second. So picture this. Your dashboards are bleeding red. Database connections are just completely dropping. And your customers? Well, they're getting 500-level errors across the entire platform. Naturally, you jump right onto the emergency incident bridge. You check the infrastructure, and it actually looks perfectly healthy. The Amazon EC2 instances are running smoothly. The network subnets are completely fine. But your application cannot read a single byte of data from the database. Last week, the executives bragged that the company finally achieved total security compliance because they encrypted absolutely everything. But right now, the engineering team is completely locked out of their own production systems. We encrypted everything and still failed. This right here is the illusion of security. People tend to think encryption is this magic shield that automatically stops hackers and just magically protects your data. But actually, it isn't. Encryption is simply a highly complex access control mechanism. Let's move to part 1, the warehouse lock metaphor, where we'll unpack this core access problem. Think about a massive warehouse, one that's holding millions of dollars of physical inventory. You go ahead and put an indestructible military-grade lock on the front door. Boom! You're safe from thieves, right? But what if you lose the only key to that lock? Or what if the lock just rusts shut? Your business still goes bankrupt because you cannot access or sell your own inventory. A warehouse secured by locks that nobody can open isn't a secure business. It's a tomb. Which brings us to part 2, AWS KMS access control. Let's take a look at the digital lock. In AWS, your lock and key system is the AWS Key Management Service, or as we call it, KMS. Now, KMS is a highly secure managed service. Its whole job is to generate and protect your cryptographic keys, and it does this securely inside FIPS-validated hardware security modules. When you encrypt an Amazon EBS volume or maybe a database, the actual data is protected by a generated data key. But it doesn't stop there. That data key itself is encrypted and protected by a top-level root key. And that root key, it never leaves KMS unencrypted. And, well, this is where the operational nightmare really begins. Because you do not just turn on encryption and walk away. You actually have to manage the access to it. Let's say your auto-scaling group boots up a new web server. That new server needs to read the encrypted database, right? To do that, the server's IAM role must have explicit permission to use the KMS decrypt action on that specific KMS key. Now, what happens if a junior engineer accidentally modifies the key policy and removes that permission? Well, the server instantly loses access to the ciphertext. The database didn't crash, the network didn't fail, you basically just revoked your own access to the warehouse. All right, part 3, key rotation versus deletion. These are your biggest operational dangers. Now, here is the mistake that most engineers never realize until it's too late. It happens during the encryption lifecycle, specifically around key rotation. If you're studying for your SOA-C02 exam, and honestly, just out in the real world, you absolutely must understand the difference between AWS managed keys and customer managed keys. AWS managed keys are controlled by the service itself, and they rotate automatically every single year. You really don't have to think about them. But when you use customer managed keys, which you do to gain total operational ownership and establish your own custom key policies, you are fully responsible for their life cycle. So what happens if you enable automatic key rotation for those customer managed keys? Operations engineers often start to panic. They think to themselves, wait, if the key rotates, do I have to take production offline to re-encrypt petabytes of database storage? The answer is no. Key rotation has absolutely no effect on the data that the KMS key already protects. Basically, KMS simply generates a new backing key version for all your future encryption operations. Meanwhile, it safely keeps the older backing keys alive in the hierarchy behind the scenes, so you can still seamlessly decrypt all your historical data. But what if an engineer decides to, quote-unquote, clean up some old customer-managed keys to save a little money?
Say they schedule a KNS key for deletion. Once that deletion window expires and the key material is destroyed, every single byte of ciphertext that was encrypted under that key becomes permanently, mathematically unrecoverable. Pause that for a second. You didn't just break the application, you permanently destroyed the company's data. Moving on to part 4, managing operational secrets, because this expands way beyond just the database. You see, encryption goes way beyond protecting your databases and hard drives. It heavily applies to your operational secrets too. Let's say you encrypt your entire database, but you leave the database login credentials sitting in plain text inside a configuration file right there on your web server. If you do that, your encryption strategy is completely fake. A hacker doesn't need to try and break your heavy-duty AES 256 encryption algorithm. Why would they? They can just read the text file, log in as the administrator, and the database decrypts the data for them automatically. That's why mature operations teams use a dedicated secrets management system. They store things like their database credentials, API tokens, and licenses securely, and then they encrypt those secrets using KMS. Let's wrap this up with part 5, the shared responsibility mindset. Ultimately, this is the operational security mindset you absolutely need if you want to survive. As an AWS SysOps administrator, you have to realize that encryption alone is not security. It is a shared responsibility. AWS provides the indestructible vault, sure, but you have to write the key policies. You have to manage the rotation schedules. You need to protect the operational secrets. And you must ensure your infrastructure actually has the correct permissions to operate. Because the brutal operational truth about encryption is this: an unbreakable lock is only valuable if you are the one who still holds the key. So do you know who holds yours? Welcome to the Explainer. Today we're talking about the seawall, defending production at the edge. We're going to dive deep into how modern cloud architecture actually survives the chaotic and honestly sometimes malicious realities of the public internet. Picture this. It's a random Tuesday afternoon, and out of absolutely nowhere, your dashboards just spike. The metrics are showing this massive coordinated traffic surge rocketing straight toward your architecture. The operations team immediately jumps onto the incident bridge, and everyone is just bracing for impact. Right away, you're expecting a major outage. You're just waiting for the web servers to completely melt down. You're waiting for those database connections to max out and for those dreaded 504 gateway timeouts to start flooding everybody's screens. We all know that feeling, right? That horrible sinking feeling in your stomach when you just know the whole system is about to fall over. So you wait, but nothing happens. The servers, they don't even flinch. The CPU utilization stays completely flat. Production never goes down. I really want you to think about that for a second. The absolute largest attack of the entire year just hit the company, and production never even noticed. We were attacked, but somehow, completely against all odds, we survived. Now, to understand how a miracle like that is actually possible, we have to look at why distributed denial of service, or DDoS attacks, work in the first place. You see, a volumetric DDoS attack doesn't try to hack your code. It's not trying to steal your passwords or find some clever backdoor into the system. It literally just tries to drown you. It weaponizes millions of compromised devices all around the world to send this massive flood of absolute junk network traffic directly to your servers. The whole goal is to exhaust your network bandwidth and your compute capacity until your legitimate paying customers physically cannot get through. Think about a massive tsunami headed straight for a coastal city. If you wait until the water is literally crashing into the downtown buildings to start fighting it, you've already lost. The city will be destroyed. You do not fight a tsunami in the streets. No, you build a massive seawall miles out in the ocean to break the wave before it ever even reaches the city. And in AWS, your seawall, that massive protective barrier positioned miles out in the ocean, is Amazon CloudFront. This is where your true defense actually begins. Here's how it works. Instead of letting users connect directly to your application load balancers, the traffic cops of your network, or your Amazon EC2 instances, which are just your virtual servers, you route your global traffic through CloudFront. Now, CloudFront is widely known as a content delivery network, mostly used for making images and videos load faster. But operationally, it acts as a globally distributed shield. It intercepts all that traffic at hundreds of CloudFront edge locations around the entire world, keeping it far, far away from your core infrastructure. So when the attack hits, it doesn't hit your single AWS region. It hits the global edge network. And sitting right there at the edge is AWS Shield. And honestly, here's the best part. Every single AWS customer gets AWS Shield Standard automatically, at literally no extra cost. It uses advanced flow monitoring to instantly detect and mitigate these large common network and transport layer volumetric attacks. It quietly absorbs the tsunami. It just drops those malicious packets at the absolute edge of the AWS network. They never travel over the ocean. They remain completely 100% invisible to your backend servers. Now, here is the mistake most engineers make. They think that surviving a volumetric attack means they're perfectly secure. But what happens if the attack isn't just dumb, brute force network traffic? What happens when the attackers actually get smart? What if it's an application layer attack? Instead of just blasting junk packets, hackers will use highly sophisticated botnets to send legitimate-looking HTTP requests directly to your login page, or maybe your search API. And because the traffic looks exactly like real user behavior, Shield Standard just lets it right through. I mean, it's doing its job after all. But then your EC2 instances try to process 1 million fake logins, and your underlying database simply collapses under the sheer weight of the queries. This leads us to another massive trap in AWS architecture, and this is a major stumbling block for a lot of engineers. It's relying on auto-scaling to save you. Engineers think that if an attack hits, auto-scaling is just going to automatically launch more instances to handle the load. But let me be absolutely clear about this. If you scale up to absorb millions of malicious bot requests, you aren't mitigating the attack. You are just bankrupting your own company by paying for the compute power to serve hackers. So to actually stop these application layer attacks, you have to deploy AWS WAF, the Web Application Firewall, and attach it directly to that CloudFront distribution we talked about earlier. Think of WAF as your intelligent bouncer standing right there at the front door. AWS WAF allows you to inspect the actual contents of the HTTP request before it's ever allowed to pass through the edge. You can write highly specific WAF rules to block requests from certain geographic countries, or instantly block IP addresses that belong to known malicious bot traffic. It essentially filters all the bad actors out, while letting your real, paying customers right on in. But I've got to say, the absolutely most powerful operational defense for an application layer attack is rate limiting. With AWF, you can set a blanket rule. Let's say, no single IP address is allowed to make more than 2,000 requests every 5 minutes. The moment an attacker's script exceeds that threshold, WAF automatically slams the door shut and returns a 429 too many requests error. And in this scenario, seeing a 429 is a massive win. It means the system is actually working. The malicious bot gets blocked right there at the edge. The database never even sees the query. The workload on your actual servers remains completely unaffected by the massive storm happening miles and miles away. And this, right here, is the mature operational edge defense strategy. You absolutely do not expose your infrastructure directly to the wild, unpredictable internet. A mature security architecture pushes the defensive perimeter as far away from the core application as physically possible. You combine CloudFront to globally distribute the load, Shield to absorb those massive network floods, and WAF to aggressively inspect and throttle the specific application requests. You know, the old mindset in IT was all about building stronger, bigger servers just so they could survive the attack. But modern cloud operations teams understand that the hero of this story is not the server. The hero is the wall that prevented the battle from ever reaching the server in the first place. Because the brutal operational truth about cloud security is this: the best outage isn't the one you recover from the fastest. The best outage is the one that never reaches production. So, taking a look at your own architecture today. Where is your defensive perimeter? Are you fighting the tsunami in the streets, or have you built your seawall?
All right, let's jump right in. I want you to picture the absolute ultimate sysadmin nightmare. Your primary EC2 dashboard, it's glowing a perfect, beautiful green. CPU utilization across your whole fleet is sitting super comfortably at 20%, memory is totally stable, and there are literally 0 locked queries in your database. Basically, everything looks absolutely flawless. But your incident response channel is completely exploding. Customers are flooding your support queues, they're super frustrated and completely unable to load the app. They're all getting hit with server not found errors. And man, that panic is really starting to set in.
So, you frantically check your application load balancers, and you realize something absolutely terrifying. They aren't even receiving traffic. The customer requests aren't timing out, they just aren't arriving at all. You and your engineers are just staring at your screens in total disbelief. Everything works perfectly, so why on earth can't anyone reach it?
Well, because the servers didn't fail, the directions failed. It's kind of like this. Think about a massive fleet of emergency vehicles dispatched to a huge raging city fire. The fire trucks are fully fueled, the engines are running, and the drivers are perfectly trained and ready to go. But the central GPS system broadcasts the wrong coordinates. It sends every single truck to an empty parking lot 3 towns away. The trucks aren't broken, the roads aren't blocked, but the building still burns down to the ground anyway, because nobody knew where to go. Think about that for a second.
And honestly, that brilliantly illustrates exactly what we're talking about today. In AWS, your global GPS system is Amazon Route 53. Route 53 is a highly available domain name system, or DNS, web service. When a user opens their browser and types in your domain name, Route 53 is the authoritative voice that translates that human-readable name into the exact IP address of your infrastructure. It's the critical, absolute front door service that actively routes the traffic to the right destination.
Now, what's really fascinating here is the disconnect. You see, Route 53 doesn't actually talk to every single individual user directly. Instead, it talks to local DNS resolvers. We're talking about servers managed by local internet service providers all around the world, from a massive telecom over in London to a regional provider down in Sydney. And this global handoff, this is exactly where the outage becomes completely invisible to your AWS dashboards.
To make the internet faster and cut down on latency, those local DNS resolvers actually cache the answers they get from Route 53. They hold on to that specific IP address for a set amount of time, which is dictated by a setting called time to live, or TTL. Now please pay close attention here, because this is where people mess up. If a junior engineer accidentally changes a Route 53 record to the wrong IP address, they might realize their mistake a minute later and quickly change it back, right? They see the correct IP in the AWS console and they think, phew, I fixed the outage. But if that original record was configured with a TTL of 86,400 seconds, well, that is an entire day.
So the absolutely crucial point here is the internet remembers the mistake. Those local DNS resolvers around the world, they've already cached those bad directions. For the next 24 hours, millions of user browsers will stubbornly route traffic into an absolute black hole, completely ignoring the fact that you already fixed the record in AWS. The local resolvers simply won't ask Route 53 for updated directions until their cached TTL officially expires. Your infrastructure is totally fine, but the downtime is real and the damage is done.
So, how do you actually survive this kind of nightmare? Well, you definitely don't rely on humans to manually update records during a full-blown crisis. You survive this by building automated operational DNS recovery right into your architecture, instead of relying on a panicked response when things suddenly go dark.
Here's how it works. You set up a primary DNS record pointing directly to your main architecture. Then you create a secondary record pointing to your disaster recovery environment. And the magic step, you attach your Route 53 health check. This health check constantly monitors your primary web server, pinging it with requests at a highly specified interval just to ensure everything is actually responding the way it should.
And that brings us to Route 53 failover routing. The very millisecond that your primary endpoint fails to respond and crosses your failure threshold, Route 53 detects it. It instantly marks the primary record as unhealthy and completely stops returning that IP address. It automatically fails over, responding to all new DNS queries with the IP address of your backup system. You didn't even touch a keyboard. You didn't have to wake up and engineer at 3 in the morning, but the global traffic instantly and automatically shifted without any human intervention at all.
Now, what if you're running a massive, multi-region architecture spanning the entire globe? For that, you use latency routing. Latency routing dynamically routes your users to the specific AWS region that provides them the absolute fastest response time. So, if a user is sitting in Tokyo, Route 53 automatically sends them to your app Northeast 1 servers, simply because it's the quickest trip. It makes total sense.
But what if your Tokyo region goes completely offline? This specific scenario, by the way, is a massive trap on the SOA-C02 exam, and it trips up a ton of engineers in the real world too. You have to know exactly what happens when a geographically close region experiences a complete and total failure.
Here is the key. If you use a latency alias record to route traffic to a load balancer, but you forget to enable a simple little setting called Evaluate Target Health, Route 53 is completely blind to the outage. It will happily just keep sending your users into the dead Tokyo region just because it is geographically closer. That's a disaster. But if Evaluate Target Health is set to yes, Route 53 looks at the alias target, realizes the fastest route is dead, backs out of that routing decision, and seamlessly shifts traffic to the next closest healthy region. It literally saves the day.
So, let's lock in these strict operational truths for SysOps administrators. Number 1, you must strictly manage your TTLs. Keep them at 60 seconds or less for critical alias records so that your failovers propagate incredibly fast. Number 2, you must instrument deep application health checks. I mean health checks that evaluate the actual health of the application, not just whether the server is powered on. And number 3, you absolutely must treat DNS as the front door to your business.
Which brings us to our final takeaway. The most dangerous, invisible outages happen when the servers are perfectly fine, but nobody knows where to go. If the GPS coordinates are wrong, it doesn't matter how powerful the servers are. The internet wasn't broken. Nobody knew where to go. So I want you to take a look at your own architecture today. What are your TTLs set to right now? And more importantly, are your directions actually pointing to safety?
Welcome to This Explainer. Today, we're diving into a real networking nightmare scenario, the ghost in the route table, and how to survive VPC isolation. Picture this. Your applications are failing. Your databases, completely unreachable. The external monitoring systems are flashing offline, and customer transactions have literally flatlined to zero. You try to SSH into the primary web server just to see what's going on, but your terminal just hangs, the connection times out, and the severity of the situation is escalating by the second. Panic starts spreading across the incident response bridge. Every engineer, every manager on that call is thinking the exact same thing. The entire company is down. But then, you look at the hypervisor metrics. The CPU utilization across your Amazon EC2 fleet is sitting at a calm 15%. The memory is perfectly stable. The servers didn't crash, your database didn't corrupt. Everything, on the inside at least, appears completely normal. The truth? The company accidentally isolated itself. The servers survived, but the network trapped them. Now, to understand how a perfectly healthy infrastructure can just completely disappear from the internet, we have to look at the architecture of an Amazon virtual private cloud. Think of your VPC like a massive, high-tech corporate building. This building is divided into secure floors, which are your subnets. And to move between those floors or to leave the building entirely, well, you need a set of directions. Those directions are your route tables. A route table is literally the master floor plan for a subnet. It dictates exactly where network traffic is allowed to go. And without it, traffic simply doesn't know how to move. In AWS, the only thing that makes a subnet public is a specific entry in its route table. If a subnet has a route sending default internet traffic, which we represent as quad 0, out to an internet gateway, then it is a public subnet. That route is the front door to the building. If you don't have that route, you are in a private subnet. Sure, you can maybe get out through a NAT gateway, but nobody from the outside can ever get in.
Now here is the networking mistake that traps even experienced engineers. During routine maintenance, an engineer is trying to clean up the network. They see a custom route table that they think is unused, so they delete it. Or maybe they accidentally disassociate it from the public subnet. What they don't realize is that when a subnet loses its explicit route table association, AWS doesn't just leave it without directions. The subnet automatically falls back to the VPC's main route table. And by default, that main route table only contains a local route. Instantly, your public subnet isn't public anymore. The front door to the building completely vanishes. The internet traffic tries to reach your application, but it hits a brick wall, right at the VPC boundary. The servers inside are screaming, perfectly healthy, but the route table has effectively bricked them up behind a wall. But the outage gets worse because the panicked troubleshooting begins. An engineer assumes the servers are actively blocking the traffic, so they check the security groups. Security groups are basically the bouncers standing directly outside a specific server's door. They are stateful. This means if the bouncer allows an incoming HTTP request from a user, they automatically remember that user and allow the response traffic to flow back out, regardless of what your outbound rules actually say. The engineer sees that port 443 is wide open on the security group. The bouncer is doing their job. So they move over to the Network Access Control Lists, or NACLs. NACLs are the security checkpoints at the elevators of the entire subnet. Now, unlike security groups, NACLs are stateless. This means they have absolutely no memory. If you explicitly allow traffic in through the NACL, it does not automatically mean the response traffic is allowed out. Desperate to fix the outage, the engineer starts tweaking the NACL, completely forgetting that when a server responds to a web request, it uses a randomized temporary return path, an ephemeral port.
Because the NACL deny behavior defaults to blocking absolutely anything not explicitly allowed, the outbound response hits the elevator and is silently dropped. So even if you fix the route table, the stateless NACL is now suffocating your application. You've got a massive subnet isolation disaster on your hands.
So how do you recover from this? In a real operational networking failure, which, by the way, is heavily tested on the AWS SysOps exam and absolutely vital for real-world survival, you do not guess. You do not blindly click around changing firewall rules. You use the VPC Reachability Analyzer. Reachability Analyzer is a static configuration tool that performs a hop-by-hop analysis of your virtual network path. You just tell it to trace the path from your internet gateway directly to your EC2 instance. In seconds, it evaluates every single route, every security group, and every NACL. It finds the exact blocking component. It tells you that the path failed because the route table is missing the internet gateway target, or maybe because an outbound NACL rule is missing the ephemeral port range. You find the broken association. You restore the custom route table. You fix the stateless return rule. Instantly, the doors unlock. Traffic floods back into the subnets. The dashboards turn green, and the company comes back to life. And this right here is the operational networking mindset. As a SysOps administrator, you absolutely must realize that in the cloud, physical cables don't fail. Software configurations do. A single bad route table association or a misunderstood stateless firewall can completely paralyze a multi-million-dollar architecture. Because the most terrifying outage isn't when your servers die. It's when your servers are perfectly healthy, but they are locked inside a building with no doors. So take a look at your own architecture today. Are your servers truly secure, or are they just waiting to be trapped?
All right, welcome everyone to this explainer. Today, we're going to dive into one of the most misunderstood and honestly most suspenseful areas of cloud networking. We are uncovering the hidden tunnels of Amazon Virtual Private Clouds, or VPCs. If you've ever felt completely bulletproof about your cloud architecture, only to get hit with a massive, terrifying surprise during an audit, you're definitely going to want to pay close attention. Let's jump right in and set the scene.
Picture this. The security audit is underway, right? And the lead engineer is feeling incredibly confident. They're reviewing the production architecture, verifying the private infrastructure. Every single backend Amazon EC2 instance is deployed securely in a private subnet. There are absolutely no public IP addresses attached, zero internet exposure. By all traditional networking definitions, these machines are totally invisible to the outside world. But then, the auditor pulls up the VPC flow logs, and the incident bridge just goes completely silent. The engineers are staring at their screens in total disbelief. Why? Because the logs show a massive, continuous stream of outbound traffic leaving those exact secure servers, heading straight out to external third-party payment APIs and public software repositories. Like the quote says, they locked the doors, but somehow people were still leaving the building.
So, we have a classic locked room mystery on our hands.
To solve this production mystery, we actually have to fundamentally change how we visualize a VPC. We need to stop looking at it just as lines of code and start thinking of it like a massive, highly secure corporate building. Because traditional networking gives us this huge false sense of security. An engineer looks at private subnet infrastructure and reads the checklist. No public IPs? Check. No internet exposure? Check. And they just assume the servers are completely invisible. But as our shocked engineering team just found out, that's an illusion.
Which brings us to the ultimate question we need to answer today. How on earth are these private servers getting out? I want you to really lean into this mystery as we break down the architecture layer by layer, starting with what is surprisingly absent.
Let's start with part 1, the missing front door. Before we can find the hidden tunnels, we gotta understand the standard exits.
In our corporate building analogy, an internet gateway is the public front door. If your servers are sitting in a public subnet, their route table has a direct path to this gateway. Anyone inside the building can just walk right out into the public street. And, if your security groups allow it, anyone from the street can walk right back in. It's totally bidirectional. But our audited servers are in a private subnet. That public front door simply does not exist for them. The route table has absolutely no connection to an internet gateway.
And here is the exact networking trap that catches almost every AWS engineer. It's the core of our whole mystery. People naturally assume that the phrase private subnet means total isolation. They think, hey, if a server doesn't have a public IP address and it doesn't have an internet gateway, it must be completely cut off from the world, right? Well, no. Lacking a public IP address does not automatically air-gap a server.
So if the front door is missing, but the servers are still talking to payment APIs on the internet,
There has to be another way out. That brings us to our first major architectural reveal, the hidden one-way tunnel.
Let's look closely at the route table for this private subnet and see what's actually under the hood. Right there, we see a destination route for 0.0.0.0/0. It's a default route. But crucially, it does not point to an internet gateway. It points directly to our first culprit.
Yep, it points to a NAT gateway. A NAT gateway is essentially a hidden one-way tunnel out of your building. It actually sits securely inside your public subnet, and it holds its very own elastic IP address. This is the tool that lets your private server reach out to the internet, say to download a critical software patch or verify a credit card transaction safely without ever needing its own public IP.
Here's how this proxy works in real time. Step 1, your private server needs to talk to the internet, so it sends its request through the route table straight to the NAT gateway. Step 2, the NAT gateway takes that packet and literally strips off your server's private IP address. Step 3, it slaps its own public elastic IP onto the packet and steps out the public front door on the server's behalf. And finally, Step 4, when the response comes back from the internet, the NAT gateway translates it and hands it safely back down that hidden tunnel to your private server.
So the big takeaway here is the difference between these two gateways. The internet gateway is your bidirectional public front door, but the NAT gateway is an outbound-only, hidden tunnel. It only tracks state for requests that originated from inside the VPC, so it simply drops any unsolicited inbound traffic. No hacker on the public internet can use a NAT gateway to initiate a connection to your private servers. They're secure from inbound threats, absolutely. But make no mistake, your private servers are definitely out there talking to the internet. Okay, mystery solved, right? The NAT gateway explains the third-party payment APIs. Well, not quite, because during that tense incident bridge, the auditor notices something else that throws a massive wrench into everything. We're moving to part 3, the missing S3 traffic.
The logs show that these private servers are also sending massive amounts of data to Amazon S3. But here is the plot twist. That S3 traffic isn't passing through the NAT gateway logs at all. Nothing. So if the NAT gateway is handling all the internet traffic, how on earth is this huge volume of S3 traffic getting out?
It's escaping through a VPC endpoint. If a NAT gateway is a one-way tunnel out to the public internet, think of a VPC endpoint as a totally private underground tunnel connecting buildings. It never even enters the public streets. When you create a gateway VPC endpoint for a service like S3, AWS automatically injects a highly specific prefix list route directly into your private subnet's route table. Let's compare these two paths, because this distinction is exactly why mature operations teams design things this way. When your private servers need to access an AWS service like S3 or DynamoDB, sure, sending it through a NAT gateway technically works, but it means you're routing sensitive data out to the public internet and back, and you are paying NAT data processing charges for the privilege. Conversely, with the VPC endpoint path, that specific prefix list route sends your data down the underground tunnel. It stays entirely on the AWS global private network. It never touches the public internet, and there is zero NAT charges.
Understanding these different paths, the front door, the one-way tunnel, and the underground tunnel, brings us to our final and most important section, mastering cloud boundaries.
Listen, this is the biggest real-world trap I see in cloud operations. Fundamentally misunderstanding your own security boundaries. Engineers will panic during an audit, just like the silent bridge we talked about earlier. They see outbound access, they falsely assume they've been breached, and in an absolute panic, they delete the route tables. And what happens? They accidentally suffocate their own applications. The backend servers can no longer reach the required external APIs, and everything breaks. The audit wasn't actually failing. The architecture was doing exactly what it was designed to do. The servers were private, yes, but they were never isolated.
If you are prepping for your SOA-C02 exam, or if you're just acting as a SysOps administrator, consider this operational design your ultimate networking cheat sheet. Rule 1. Use an internet gateway to let the world in. Rule 2. Use a NAT gateway to let your servers safely reach out. And Rule 3. Use VPC endpoints to access AWS services completely invisibly. You simply cannot just look at the name of a subnet and assume you know what it does. You have to read the route tables.
And that brings us to our final, absolutely crucial takeaway. I want this burned into your brain long after this explainer is over. A private subnet design is not an air-gapped vault. In cloud networking, locking the front door doesn't secure the building if you leave all the hidden tunnels wide open. So before you sign off for the day, I have to ask,
Do you actually know where your private route tables are pointing right now?
Okay, let's dive right into this explainer. Imagine it's launch night for your brand new hybrid cloud architecture. Your engineering team has spent months building this massive, highly scalable environment in AWS, right? It's designed to process all the data generated by your on-premises data center. And the deployment goes absolutely perfectly. The Amazon EC2 instances boot up, the database is initialized, everything on your dashboard is green. Then, you trigger the initial data sync. You sit back, fully expecting the cloud to chew through that data in seconds. But instead, the progress bar barely even moves. You look at the metrics, kind of confused, and your CPU utilization is sitting at exactly 2%. Your powerful cloud servers are just sitting there, completely idle, waiting for data to arrive. Now, what's really interesting here is that the bottleneck isn't at all where you think it is. The application isn't timing out, but the latency has completely skyrocketed. Every single API call between the cloud and the data center is taking an agonizing hundreds of milliseconds. You move to the cloud for speed. So why is everything suddenly crawling? Think about that for a second. So here's the crucial point. You didn't misconfigure your servers. Actually, you ran headfirst into a massive throughput bottleneck. To understand exactly how this happens, and by the way, this is heavily tested on your SOA-C02 exam, you really have to understand how hybrid cloud networks physically communicate. When an organization wants to connect their private on-premises data center to an Amazon virtual private cloud, the absolute fastest and easiest way to do it is by setting up an AWS site-to-site VPN. You just configure a customer gateway device in your data center, you attach a virtual private gateway or transit gateway to your AWS environment, and you establish 2 encrypted VPN tunnels. It's secure, it's reliable, and honestly, you can build the whole thing in an afternoon.
That there is a massive operational trade-off here. A site-to-site VPN runs over the public internet, and the public internet is not a direct cable. It is a chaotic web of third-party internet service providers, dynamic BGP routing changes, and wildly unpredictable traffic spikes. When you try to send terabytes of data over a VPN, your packets are bouncing across multiple hops, literally fighting for bandwidth with everyone else on the planet.
And this analogy brilliantly illustrates the core issue. Think about building a pristine 10-lane superhighway in the cloud and another 10-lane superhighway in your data center. But to connect them, you force every single car to exit and drive down a 1-lane dirt road through a crowded city. It really doesn't matter how fast your servers are. That dirt road chokes everything. Now here's the networking bottleneck that almost nobody sees coming. Engineers often assume that if they just buy a bigger internet connection for their data center, the VPN will magically get faster. But a VPN connection to AWS has hard throughput limitations per tunnel. When you hit that ceiling, your packets just start dropping. The network violently throttles your application, creating massive operational latency that completely paralyzes the business. We're talking real downtime and lost money here. So, to fix this, you have to bypass the internet entirely. This is where AWS Direct Connect absolutely changes the game. Direct Connect is not just some software configuration over the internet. You use Direct Connect to create a dedicated, physical private connection from your remote network straight into your VPC. Your traffic never touches the public internet. It never has to fight for bandwidth. When you provision a Direct Connect line, you are essentially buying a massive, dedicated pipe just for your business. Because the route is direct and uncontested, your operational latency drops from those unpredictable hundreds of milliseconds down to a stable, consistent, single-digit millisecond response time. Suddenly, your hybrid cloud behaves exactly as if your data center and your AWS environment are sitting in the exact same room. But here is the ultimate real-world and exam trap. And trust me, this is where people mess up. Direct Connect relies on physical infrastructure. And physical cables get cut, backhoes dig up fiber lines all the time, data center routers lose power. If your entire business relies on a single Direct Connect link, and that link goes down, your hybrid cloud is instantly severed, your company is totally isolated. A mature SysOps administrator never, ever relies on a single point of failure. To build true operational resilience, you have to design for disaster. You can connect your virtual private clouds and on-premises networks using a transit gateway which acts as a central hub routing traffic between VPCs, VPN connections, and direct connect connections. You provision your high-speed direct connect line as your primary path, but then you configure an AWS site-to-site VPN as a fallback backup system. Under normal conditions, your massive data syncs flow effortlessly over that dedicated fiber. But if that physical line gets cut at 3 a.m., your BGP routing dynamically detects the failure and instantly shifts your traffic over to the encrypted VPN tunnels. Yes, the VPN is slower, yes, the latency will increase, but the business survives. Of course, you must actively monitor this connectivity. When you connect by using Direct Connect, you can use synthetic monitors in Network Synthetic Monitor to proactively monitor network connectivity. It does this by running synthetic tests between a VPC and your on-premises endpoints. These tests are absolutely crucial because they detect issues with connectivity, DNS, and latency way before they ever impact your actual applications. Ultimately, this is the operational networking mindset. In the cloud, we don't just build fast servers. We build resilient pathways. Because the most powerful, infinitely scalable cloud architecture in the world is completely useless if the data cannot actually reach it. As the saying goes, your servers can only run as fast as the network allows. So ask yourself, if a backhoe cuts your primary fiber line tonight, does your architecture ensure your business survives the shift, or does your entire operation go dark?
Let's jump right into this explainer. I want you to picture a scenario. It's the absolute biggest global product launch in your company's history. Literally, everything is on the line. You've got your entire backend deployed in the US East 1 AWS region out in Northern Virginia, and your database, it is perfectly tuned. Your auto-scaling groups are just humming along beautifully. You're watching the traffic start to roll in from the East Coast of the US, and the application is incredibly snappy. We're talking load times well under 200 milliseconds. It looks like a massive total success.
But then, the complaints start flooding in on social media. Users in Tokyo, Sydney, and London are absolutely screaming. For them, the website isn't snappy at all. Actually, it's taking 7, 8, or even 9 seconds just to load the homepage. Images are loading line by painful line. The checkout button is timing out entirely. Naturally, panic sets in. You rush to check your Amazon EC2 instances, completely expecting them to be redlined and overloaded. But they're practically sitting idle. Your infrastructure is perfectly healthy. The servers are incredibly fast, but the speed of light, well, the speed of light is just too slow.
And this perfectly illustrates the absolute core problem of global networking, because even with the most advanced fiber optic cables on the planet, data takes physical time to travel across the Pacific Ocean. If a user in Sydney opens your website and that single web page requires 40 separate HTTP requests to load up all the images, the style sheets, the scripts, that user is forced to make 40 full round trips across the entire globe. Those tiny, imperceptible milliseconds, they start to compound into long, incredibly frustrating seconds. Think about that for a second. At a truly global scale, the sheer physical distance between the user and the server is your ultimate enemy.
So to survive this kind of global load, you have to stop forcing your global users to travel all the way to your servers. Instead, you have to move the servers directly to your users. And that brings us to the ultimate solution, Amazon CloudFront. CloudFront is the AWS Content Delivery Network, or CDN for short. It's the specific tool engineered from the ground up to completely eliminate that geographic distance. To really wrap our heads around this, think about a massive, world-famous bakery, right? If they only have one giant mega kitchen located in New York, a customer in Tokyo ordering a fresh pastry is going to wait days for shipping. And by the time it finally arrives, it's completely stale. But what if that bakery opens 1,000 tiny franchise storefronts in every major city on Earth? The mega kitchen simply ships the pastries to the local stores overnight. So the next day, that customer in Tokyo walks in, gets the exact same pastry instantly, and never even realizes it didn't come directly from New York.
Let's map this back to our AWS architecture. In the AWS world, those local franchise storefronts are called CloudFront Edge locations. CloudFront is basically a globally distributed network made up of hundreds of points of presence all over the world. When you place CloudFront in front of your architecture, you fundamentally change how your content gets delivered. When that first user in Sydney requests your company's logo, the request doesn't travel all the way back to Virginia. It gets intercepted right there at the local Sydney Edge location. Now, because it's the very first request, the Sydney Edge location doesn't actually have the logo yet. So it reaches back to your primary server, which we call the origin, downloads the file, serves it to the user, and then caches it locally. Here is where the magic happens. When the next 100,000 users in Sydney request that exact same logo, CloudFront doesn't even bother asking your Virginia servers. It just serves the cache file directly from Sydney in single-digit milliseconds. The traffic literally never crosses the ocean. It makes the internet feel instant.
Section 1. The cache invalidation trap, or exactly where operations teams completely break their own websites.
Okay, imagine this. The marketing team notices a glaring typo on the homepage banner image during a massive promotion. They panic, quickly upload a new, corrected image to the Amazon S3 origin bucket using the exact same file name, and they refresh their browsers. But the typo is still there. They frantically refresh again. Still there. Now they're screaming at the operations team, demanding to know why the website won't update. Well, the crucial point here is they didn't understand the cache lifecycle. You see, CloudFront holds onto cached files based on a specific setting called time to live, or TTL. If your TTL is set to 24 hours, that edge location is going to stubbornly serve the old broken image to the entire world for a full day, completely ignoring the shiny new file you just uploaded to S3.
So, to fix this massive emergency, you have to trigger what's called a cache invalidation. Basically, you are manually instructing CloudFront to hunt down that specific file across every single edge location globally and violently purge it from the cache. But listen carefully here. Invalidations take time to propagate. If you're relying on them as your normal day-to-day deployment strategy, you are failing operationally. A mature SysOps administrator doesn't rely on panic invalidations. Instead, they use version file names, something like banner_v2.jpg. That way, when the underlying HTML updates, the user's browser requests a brand new file which completely bypasses the old cache automatically. It's a much safer way to operate.
And this actually leads us directly into another massive real-world trap: accidentally caching dynamic content. If you mistakenly misconfigure your CloudFront cache behaviors, you might accidentally end up caching a user's private shopping cart, or even worse, their personal account dashboard. Just think about the absolute disaster here. The next person who logs in halfway across the world might get served that first user's cached banking details. You absolutely must strictly separate your static assets, which are perfectly safe to cache for weeks, from your dynamic API calls. Those dynamic calls absolutely must be configured to pass straight through to the origin immediately, without any caching whatsoever.
Now, I want to ask you a really critical question. What happens if your primary origin completely dies? Like, what if that US East 1 region experiences a massive failure and your EC2 web servers go completely dark?
Well, this is exactly where CloudFront transforms from just a simple speed tool into an absolute disaster recovery weapon. You can configure something called CloudFront Origin Failover. Basically, you set up a primary origin pointing to your main load balancer, and a secondary origin pointing to a static S3 bucket that hosts the maintenance page or even a lightweight backup site. If CloudFront tries to fetch content from the load balancer and receives a 504 gateway timeout, it doesn't pass that terrifying error on to the customer. Instead, it instantly and invisibly fails over to the S3 bucket and serves the backup content. Even better, if you configure your cache correctly, CloudFront can continue serving stale, cached content to your global users while your back-end engineers are frantically trying to revive the database. Your users might not even know you're having a massive outage.
And really, this brings us to the broader operational mindset for content delivery. We don't just use CloudFront to make images load faster. Honestly, that's just the tip of the iceberg. We use it to physically shield our origins from massive traffic spikes. We use it to enforce encryption at the absolute edge of the network. And we use it to strictly isolate failures, ensuring that a disaster in one single data center doesn't ripple out and bring down the entire global user experience.
Which brings us to the final major takeaway of this entire explainer, because the ultimate operational truth about speed and resilience is simply this: the fastest, safest way to serve a customer request is to never let that request reach your server in the first place. Think about that for a second. So take a hard look at your own architecture today. How many of your servers are working desperately hard right now to process requests that never ever should have reached them in the first place?
Picture this. It's 7 o'clock on a Monday morning, and you've just poured your first cup of coffee. Suddenly, a frantic message from the finance director pops up on your screen.
Your stomach instantly drops, right? You open the message, bracing yourself for the worst. But what you see is actually not a screenshot of a server error. There's no database panic, no 500 gateway timeout. Instead, it is a screenshot of the AWS billing console.
And the numbers on that screen are absolutely horrifying. Your company's monthly cloud bill, which usually hovers right around a very predictable $2,000, just hit $48,000 over a single weekend. Think about that for a second. That is a massive, completely unexpected financial loss.
So let's get into Section 1, Anatomy of a Silent Bug. You immediately jump onto the incident bridge. You start frantically pulling up all your monitoring dashboards, fully expecting to see a massive disaster unfolding. You're bracing yourself for red alarms, failing databases, and offline services. But everything is completely green. The Amazon EC2 instances, they're running perfectly. The load balancers are routing traffic exactly as they should. Customers are happily using the platform without a single complaint. There are absolutely zero outage alerts firing in your Slack channels.
Which leads us to a massive paradox, doesn't it? How on earth did the bill explode overnight if nothing actually broke? Well, you dig deep into the logs and you finally find the answer. You discover that late on Friday night, a junior developer pushed what was supposed to be a minor update to a background worker process. But that update introduced a silent, entirely invisible bug. It was an infinite retry loop. Every single time a specific background job failed, the system instantly retried it, and then it failed again, and it retried again, on, forever. And the craziest part? The impact was completely invisible to your uptime metrics. The job was failing thousands of times per second, but the application itself remained highly available. The infrastructure was actually doing exactly what you designed it to do.
But here is exactly how that seemingly harmless bug builds into a disaster. Amazon EC2 auto-scaling saw that massive spike in CPU utilization caused by the infinite retry loop, so it triggered your target tracking policy and happily launched 20 new, highly expensive instances just to absorb the fake load. At the exact same time, Amazon CloudWatch logs ingested terabytes of error messages from those failures, effectively charging you heavy data processing fees for every single gigabyte.
So the absolutely crucial point here is this. The company did not suffer a technical outage. It suffered a financial outage.
Think about a massive water leak hidden completely behind the drywall of your house. You don't see any puddles in the living room. The lights are on, the TV works, and the house feels completely normal. But outside, your water meter is spinning at maximum speed. By the time you finally get the water bill a month later, you are completely bankrupt.
And that brings us to a fundamental truth of modern engineering. In the cloud, your infrastructure is the water. If you don't monitor the meter, it will quietly drain your bank account.
Which leads us to Section 2, the trap of traditional monitoring, missing cost signals. Now here's the truly terrifying part that most engineers never realize until it's too late.
When engineers design monitoring systems, we obsess over CPU utilization, memory limits, database locks, and HTTP error codes. We diligently monitor the technology itself. But we completely forget to monitor the cost as a core operational signal. This is exactly where people mess up.
A perfectly working infrastructure can still be actively failing the business. Think about it. If your code is inefficient, if you leave unattached Amazon EBS volumes just sitting there idle, or if your auto-scaling group scales up during a spike but fails to scale back down, that is all operational waste. And in the cloud, waste is billed by the second.
All right, Section 3, stopping the bleeding, finding the leak. So when you're in the middle of this nightmare, how do you recover? How do you actually stop the bleeding?
Well, you can't just guess what service is burning the money. You immediately open AWS Cost Explorer. You filter the view by the last 3 days, and crucially, you group the costs by service and usage type. Instantly, the picture becomes clear. You see a massive red spike in EC2 compute charges and CloudWatch data processing bytes. From there, you isolate the specific resource tags. You found the leak. You immediately terminate those rogue auto-scaling instances, you deploy a hotfix to break the infinite loop, and finally, the bleeding stops.
Let's move to Section 4, Proactive Safety Systems, Proactive Controls. Because the real question is, how do you prevent this exact scenario from destroying the company next month? You absolutely have to build financial safety systems directly into your operations.
First up, you create a CloudWatch billing alarm. But listen up, because here is a massive trap for both your SOA-C02 exam and your real-world deployments. Before you can even create a billing alarm, you must change your AWS console region to US East, Northern Virginia. Even if your entire infrastructure and all your servers are running in Tokyo or London, AWS global billing metric data is only stored and evaluated in the N Virginia region.
Once you're in that correct region, you configure a static threshold. You set it up so that if the estimated charges metric exceeds your normal baseline by even $500, the alarm instantly triggers an Amazon SNS topic and immediately pages the operations team.
But look closely at this distinction because it's vital.
A billing alarm only tells you after the money is already spent. To get truly proactive, you have to implement AWS budgets. With AWS budgets, you define strict cost thresholds, but instead of just tracking what you spent today, AWS budgets actually evaluates your forecasted costs.
This means if your sudden scaling trajectory predicts that you are going to blow past your monthly budget limit by next Tuesday, AWS Budget sends the alert right now, giving you time to act.
And you can take it a step further. You can even attach automated budget controls to achieve the ultimate level of safety. For example, if a development account suddenly spikes in cost, an AWS budget action can automatically execute an IAM policy that strictly restricts anyone from launching new EC2 instances until that budget is formally reviewed.
Ultimately, this is the reality of modern cloud engineering. You are not just a systems administrator making sure the servers stay online anymore. You are a financial gatekeeper. AWS budgets and billing alarms are not just handy tools for the finance department to look at. They are absolutely critical operational safety systems. Because an architecture that bankrupts the company just to keep a broken application online is not a successful deployment.
Which leaves us with this final provocative thought. The server survived, but the bill didn't.
Okay, let's dive right into this explainer. Picture this scenario for a moment. You're sitting in the engineering bullpen, and the CFO walks in. The room gets a little quiet. The quarterly profit margins just dropped again, and guess what? Your AWS bill is the prime suspect. As the lead engineer, you immediately feel that knot in your stomach. So you pull up the dashboards, fully expecting an absolute disaster. You're bracing yourself for red alarms, database deadlocks, cascading 504 gateway timeouts, the whole shebang. But you look at the screen and honestly nothing makes sense. Production is absolutely flawless. You're seeing 0 dropped packets, 0 latency spikes, literally 100% uptime. Your customers are perfectly happy and the applications are undeniably healthy. So the technical side of the house is shining, but the financial side, it's bleeding. So you really have to ask yourself this critical question. Where is the money going? Think about that for a second. You have a perfect system, but a completely out-of-control budget. Naturally, you dig into Amazon CloudWatch to find out what's really going on. And right there, looking at your Amazon AC2 fleet, you find the silent killer, 2%. You have hundreds of backend servers, and we're talking massive, memory-optimized, compute-heavy instances here. But their average CPU utilization, it's sitting at a flat 2%. They are practically asleep. So why did this happen? Well, it happens because engineers are terrified of traffic spikes. During the initial launch, the team over-provisioned absolutely everything, just to be safe. They bought the biggest servers possible, and they simply never looked back. To put that into perspective, think about renting a massive, state-of-the-art stadium designed for 10,000 people just to host a daily event. But every single night, only 50 people actually show up. Sure, the event is a success, nobody gets hurt, and everyone has a great time, but you still have to pay the rent for those other 9,950 empty seats. That is exactly what's happening in the cloud. You are paying top dollar for massive capacity that literally nobody needs. So the crucial point here is the fundamental difference between technical health and financial health. In real production environments, engineers are trained to obsess over uptime and performance. When an operations engineer sees a server running at 2% CPU, they usually smile. They think they've built this highly resilient, bulletproof system with plenty of headroom, but they completely ignore utilization efficiency. They just don't realize that a healthy infrastructure can still be financially unhealthy. Because if your server is 98% idle, you're throwing 98% of your compute budget straight into the trash, every single hour of every single day. Section 1. Finding the financial leaks. Look, you cannot fix operational waste if you can't even see it. So let's look at how to actually stop this bleeding. To do that, we need to run an audit of the environment. To find these leaks, you start by opening AWS Trusted Advisor. Think of Trusted Advisor as your automated cloud expert that constantly scans your entire environment against strict best practices. If you look at the cost optimization pillar, it immediately flags dozens of low-utilization Amazon EC2 instances. It shows you exactly which servers have had less than 10% CPU utilization for the last 14 days. But here's the catch. Trusted Advisor just tells you that a server is too big. It doesn't actually tell you what size it should be. And you really don't want to guess, scale down too far, and accidentally cause a massive production outage. So to remove that guesswork entirely, you activate AWS Compute Optimizer. Compute Optimizer is a real game changer because it takes the guesswork completely out of cost efficiency. It uses advanced machine learning to analyze your historical CloudWatch metrics, looking at your CPU, memory, and network throughput over time. It doesn't just broadly say scale down, it gives you a highly specific architectural recommendation. It tells you confidently, okay, you're currently running an M5.4x large. Based on your historical actual workload, if you migrate to a T3.medium, you'll maintain perfect performance during your peak hours, and you will save 82% a month.
And this brings us right to the core concept of right-sizing. Right-sizing is simply matching your underlying infrastructure to your actual operational demand. And notice what we are not doing here. You aren't deleting the application, you aren't rewriting a single line of code. You are just ensuring that your operational alignment actually makes financial sense.
So how do we actually execute this in the real world? Well, it takes 3 systematic steps. First, you modify your autoscaling group launch templates with those newly recommended instance types. Second, the massive, oversized instances are systematically terminated by the system. And third, the smaller, highly efficient instances boot up and seamlessly take their place. You are systematically replacing that wasteful infrastructure with right-sized instances, all without ever taking the system offline.
And the result? Well, the next month, the CFO walks back into the engineering bullpen, but this time, it's good news. The total AWS compute bill just dropped by 40%. The application is still running perfectly, the load times are exactly identical, the customers haven't noticed a single thing, but your bottom line has drastically improved.
Section 2, Achieving Operational Efficiency. This really gets down to the mindset of true operational efficiency. A mature SysOps administrator knows that keeping the servers online is really only half the job. The other half, it's protecting the business itself. Because an architecture that bankrupts the company just to process a trickle of traffic is ultimately a failed architecture.
The infrastructure in our story was perfectly healthy, but the servers were just sitting there. The servers were busy surviving, but the money was busy leaving. Think about your own infrastructure today and ask yourself, which one is happening to you?
Welcome to today's explainer. Let's just jump right into it. I want you to picture a scenario that literally strikes fear into the heart of every IT professional. It's the middle of the day, peak traffic, and suddenly the application is just crawling. It's totally bogging down. Users are absolutely flooding your support channels, right? They're complaining about constant timeouts and, those endlessly spinning loading screens that everyone hates. Within minutes, executives jump onto the incident bridge. They are demanding immediate answers. The tension is incredibly high, the clock is ticking, and the pressure is completely on.
So the frantic engineers immediately pull up their basic dashboards. They're looking for the culprit, and right away, a massive red flag jumps out. The back-end Amazon EC2 fleet has its CPU utilization pegged at 99%. Application threads are locking up left and right. Naturally, they immediately blame the servers. I mean, everyone on the call assumes the compute layer is overloaded, especially because the company is actively losing money. And every single second of this downtime is hitting the bottom line hard.
So what happens next? Well, they do what most teams do, in a blind panic. They blindly scale up. They rush into the AWS console, they update the auto-scaling group, and they just start launching more instances. When that doesn't instantly fix it, they migrate to larger, much more expensive, compute-optimized instance types. They are quite literally throwing thousands of dollars of raw compute power at the problem, just hoping it goes away. But after those shiny, super expensive new servers boot up, performance barely improves. The application is still painfully, unacceptably slow.
And this brilliantly illustrates the core mystery we're unraveling in our explainer today. If throwing massive amounts of compute power at the application didn't fix the 99% CPU usage, then, if the servers aren't the problem, what is? Think about that for a second.
Section 1. The Investigation. Okay, to find out what was really happening under the hood in CloudWatch, we need to understand what we're actually looking for. The engineering team realizes that guessing is just wasting time and money, right? So they launch a much deeper investigation. They completely leave those high-level basic application dashboards behind. They stop looking at the compute layer entirely, and instead, they pivot to the storage layer. To understand this, let's use a really simple analogy. Think about a massive, state-of-the-art factory. Imagine you just spend a fortune buying 500 incredibly fast, highly efficient robots to assemble your products. They work at absolute lightning speed. But to get those finished products out the door and onto the delivery trucks, every single item has to travel down one tiny, extremely slow conveyor belt.
It absolutely does not matter if you go out and buy 500 more robots. The factory will not produce goods any faster. The entire system is only as fast as its absolute slowest component. Yeah, this is exactly where people mess up. It comes down to something called CPU wait time. When a server is desperately waiting for a hard drive to read or write data, the application processes begin to stack up. They have nowhere to go, so the CPU gets stuck managing this massive growing queue of blocked waiting requests. On a basic dashboard, this looks exactly like a CPU bottleneck. It screams 99%. But the CPU isn't actually doing any heavy computational lifting. It's literally just standing around, holding a clipboard, waiting for the storage disk to finally answer. So, the absolutely crucial point here is that this isn't just some theoretical issue. Whether you're taking your AWS Certified SysOps Administrator exam, the SOA-C02, or you're dealing with real-world production outages, scenarios will frequently hide the real bottleneck. The dashboards will show you high CPU utilization specifically to trick you into adding more EC2 instances. But as we just learned from our factory analogy, scaling your compute layer does absolutely nothing if your storage layer is suffocating. To prove this, the team needs specific data.
Inside CloudWatch, the engineers finally hone in on the Amazon Elastic Block Store, or EBS metrics. They start analyzing 3 very specific data points: volume read ops, volume write ops, and crucially, volume queue length. They're looking directly at the performance of the hard drives attached to their servers, and right there in the charts, they finally find the hidden killer.
Here's what happened. The EC2 instances were attached to general-purpose EBS volumes. Now, general-purpose volumes are great, but they have a hard physical limit on IOPS. That's input-output operations per second, and a hard limit on total throughput. It turns out a brand new application feature was trying to write 20,000 database transactions a second, but the general-purpose EBS volume was physically capping those writes at just 3,000. The disk simply could not spin any faster.
Because of that massive gap between 20,000 requested writes and only 3,000 allowed writes, the storage latency completely exploded. The operations frantically queued up in the system, and because they queued up, the servers locked up. The compute layer was totally fine. It was just frozen, waiting on the disk. The servers were blamed for a crime they simply didn't commit.
Section 2. Targeted Operational Tuning.
So how do you actually recover from a storage bottleneck like this without wasting thousands of dollars on compute power you don't even need? Well, you stop guessing and you perform targeted operational tuning. The very first step is fixing the actual bottleneck at the disk level. You don't add more EC2 instances. Instead, you modify the EBS volume configuration itself. By migrating from a general-purpose volume to a provisioned IOPS volume, you can explicitly dial in the exact IOPS and throughput performance your specific application demands. You're essentially widening that slow conveyor belt, granting the storage layer the exact bandwidth it needs to survive the traffic spike.
But there's a second hidden trap you really have to watch out for, and that is improper instance sizing. Listen to this. Every single EC2 instance type has a maximum dedicated EBS bandwidth limit. It's essentially the pipe connecting the server to the disk. If you attach a wildly fast, incredibly expensive, provisioned IOPS EBS volume to a tiny baseline EC2 instance, the network connection between the instance and the storage gets throttled before the disk even breaks a sweat. To fix that, you simply upgrade to an instance class that is specifically optimized for high storage network throughput, ensuring the pipe is as wide as the disk is fast.
So the engineering team applies this targeted storage tuning. And the results? They are immediate. Within seconds, the volume queue length drops to 0. The read and write latency flatlines right back to normal levels. Because the disk can finally process the data, that huge backlog of application threads instantly clears out. And as if by magic, the CPU utilization on those servers drops from a screaming 99% down to a perfectly healthy 20%. The application speed instantly returns to normal.
Section 3. Prevention. Now, recovering from the outage is great, but a true SysOps administrator knows the job isn't done yet. You have to put proactive measures in place. The team needs to ensure this specific nightmare literally never happens again. To achieve this, the engineers go right back into CloudWatch, but this time, instead of just reading past metrics, they configure automated CloudWatch alarms. Specifically, they set alarms on EBS latency and IOPS utilization. By setting these exact alert thresholds, the system will actively warn the engineering team long before the storage subsystem ever hits its physical limits again. They'll get a warning when the disk hits 70 or 80% capacity, giving them plenty of time to tune the storage before the application ever slows down.
And this brings us to the real core of operational troubleshooting.
As an administrator, or an engineer, or a developer, you cannot just look at a slow application, see a high CPU metric, and blindly assume you need bigger servers. You have to trace the data path from start to finish. You always have to find the absolute slowest component in the system.
Because as we saw in today's explainer, jumping to conclusions can cost you critical downtime and literally thousands of dollars in wasted infrastructure. You have to look deeper than the dashboard. Because in this case, the servers weren't slow. They were waiting. Think about that for a second.
Picture this. The CFO storms into the engineering meeting. They just had dinner with the CFO of a direct competitor, and they discovered a terrifying financial secret.
Your company and this competitor are running nearly the identical AWS architecture. The applications are practically the same. The daily traffic is the same. The backend infrastructure is the exact same. Yet, your company is paying vastly more money every single month.
You look at the dashboards, the servers aren't overloaded, the memory isn't leaking, the applications are perfectly healthy. So, how is that possible?
The engineering team launches a massive investigation. They dig deep into the billing console and they discover the brutal truth. The company didn't suffer a technical outage, it suffered a pricing strategy failure. See, for years, the engineering team has been paying the default on-demand pricing for absolutely every single server they launched. Think about renting a car. If you need a vehicle for a 3-year cross-country road trip, you do not walk up to the rental counter every single morning and pay the daily walk-up rate. That would bankrupt you. You sign a long-term lease. You get the exact same car, you drive on the exact same roads, but you pay a radically different price.
Now, here's the mistake most engineers don't even realize they're making. On your SOA-C02 exam and in real production environments, engineers obsess over optimizing infrastructure performance. They tune the CPU, they right-size the memory, and they carefully configure their auto-scaling groups. But they completely ignore the underlying pricing models.
They assume that if the servers are fast, the architecture is perfect. But the most expensive architecture is not always the best architecture.
To recover from this financial disaster, the operations team has to analyze the scaling economics of their workloads. They stop treating all servers exactly the same, and they begin categorizing them based on operational cost trade-offs.
First, they look at their highly predictable workloads. We're talking the core backend systems and the baseline web servers that never ever turn off. For these, they purchase reserved instances. By committing to a usage term, you can pay for usage up front to get significant discounts for on-demand instances. With reserved instances, your discounted rate applies if Amazon EC2 autoscaling launches matching instance types.
But there is a catch. Reserved instances lock you into specific instance families. So, what if the team wants to upgrade to a newer processor next year?
This is exactly where they apply savings plans for their flexible workloads. With savings plans, your discounted rate applies when using Amazon EC2 instance savings plans or compute savings plans.
You get massive discounts, but with savings plans, you have much more flexibility when prioritizing your instance types. You can change instance sizes or shift AWS regions without losing your financial benefit.
But the biggest savings? Those come from the fault-tolerant workloads. The engineers look at their background workers, their batch processing jobs, and their stateless web servers. These applications really don't care if a server suddenly reboots. So, the team migrates them to Amazon EC2 Spot instances. Spot instances provide you with access to unused EC2 capacity at steep discounts relative to on-demand prices. They are a cost-effective choice if you can be flexible about when your applications run, and, crucially, if your applications can be interrupted.
And that is the massive operational trade-off. Amazon EC2 can terminate an individual Spot instance as the availability or price for Spot instances changes. If you run a rigid, fragile application on a Spot instance, your production environment will crash.
But because the team properly identified their fault-tolerant workloads, they survive the interruptions seamlessly. When a Spot instance is terminated, the autoscaling group simply attempts to launch a replacement instance to maintain the desired capacity for the group.
The engineering team updates their auto-scaling groups to use a mixed instances policy, brilliantly combining the rock-solid reliability of on-demand instances with the massive discounts of Spot instances.
The very next month, the AWS bill drops dramatically. The application is exactly the same. The latency is exactly the same. The customers haven't noticed a single difference. The engineers learned that true cloud optimization isn't just about managing CPU cycles. It is about deeply integrating AWS pricing models directly into the infrastructure design.
The architecture never changed. The price did.
All right, let's dive right into this. Welcome to today's Explainer. Today, we're unpacking something absolutely crucial, the true architecture of autonomous resilience. We're going to break down exactly what it takes to build cloud systems that can survive, well, total chaos. And more importantly, we'll talk about the fundamental mindset shift you need to actually get there. So, let's jump right in. Picture this. It's 3 a.m. on a Sunday. You're dead asleep. Suddenly, your phone starts absolutely screaming. You're a junior cloud engineer, and your primary production database is crashing hard. Customers are getting slammed with 500-level errors, and active transactions are just dropping like flies. So you jump out of bed, your heart's pounding, you log into the AWS console, and you frantically start running emergency scripts. You reboot the frozen instances, you manually redirect the application traffic over to a read replica, and finally, by 6 a.m., after hours of agonizing downtime and thousands of dollars in lost revenue, the system is stable. On Monday, you walk into the office feeling like an absolute hero. You're thinking, wow, I am a phenomenal cloud engineer.
But here's the reality check. A mature operations team, they look at that weekend and they don't see a hero. They see a massive, catastrophic failure of systemic design. Because guys, the ultimate goal of operations isn't to be the superhero who swoops in and fixes broken systems in the middle of a night. Not at all. The goal is to build a system where the failure fixes itself before you even wake up.
And this brings us to the operational mindset that literally every cloud engineer needs to internalize. There's a ladder here. 4 distinct levels of operational maturity in the cloud. Level 1 is basically survival mode. Things break and you only find out because your angry customers report the outage. Then level 2 is reactive. Your monitoring actually detects the failure, but it still pages a human engineer to come fix it. Moving up, level 3 is proactive. This is where engineers use telemetry data to predict a failure and fix it before the customer ever even notices. That's good. But level 4? Level 4 is autonomous. This is where the systems automatically recover entirely on their own, with zero human intervention.
Now, to actually reach level 4, you have to completely change how you look at AWS. Beginners study the cloud by just memorizing services, but true elite operations, that's about understanding exactly why those services exist and when to apply them so your system survives total chaos. You really must accept a brutal, kind of uncomfortable philosophy here. Ready? Failure is expected. It is not exceptional.
Look, hardware degrades. Networks drop packets all the time. Instances randomly reboot. That's just reality. If your architecture requires every single piece of hardware to work perfectly 100% of the time just to stay online, well, your architecture is already broken. You have to practice reliability engineering. Think of it this way. You don't try to stop the rain. You build a waterproof house. Let's use a commercial airplane as an analogy. A single engine failing mid-flight? That is not a catastrophic system-ending disaster. It's actually a known design parameter. That plane is explicitly engineered to keep flying perfectly fine on the remaining engines while the pilots safely land the aircraft.
And that right there is the absolute fundamental difference between reliability and resilience. Listen closely to this distinction. Reliability means the plane takes off, flies, and lands safely under normal, sunny, ideal conditions. Resilience is how that same plane behaves when an engine literally explodes at 30,000 feet. In the AWS world, deploying your application to a single availability zone might be highly reliable for months. It might run perfectly, but it is absolutely not resilient. Deploying across multiple availability zones, backing it up with an auto-scaling group that automatically terminates and replaces a dead instance without a human ever needing to ask for permission, now that is resilience.
I really want you to think about that for a second. Let it sink in. We do not build resilient systems to prevent failure. That's impossible. We build them so that when failure inevitably happens, the customer never even notices.
Now, in just a moment, I'm going to share the single most important question elite operations teams ask before any deployment. But first, we have to talk about curing operational blindness. The deadliest trap, the one that catches almost every engineer moving to the cloud, is sitting around waiting for their infrastructure to tell them it's broken. Guys, you cannot operate a system if you are blind. Observability is the absolute bedrock for understanding your system's behavior. A mature cloud engineer instruments literally everything. They use Amazon CloudWatch, AWS X-Ray, VPC flow logs, and not just to hoard data. They use them to gain deep, actionable insights into the actual heartbeat of the application. And here's the kicker. They do not set alarms on lagging indicators. A 504 gateway timeout? That's a lagging indicator. It tells you the system is already dead. Instead, they set alarms on leading indicators, like a shrinking database connection pool or a sudden spike in disk queue length. Think about the difference there. A beginner gets a blaring, panic-inducing alert that the server is dead. A mature ops engineer, they get a quiet little alert that a server will die in 20 minutes and that their automation has already started spinning up its replacement.
Which brings us to a massive, massive trap. You'll see this on your SysOps exams, and you will definitely see it in real-world production environments. And listen, this is where people mess up. The trap is manual intervention. Whenever a scenario asks you how to recover from a drifted configuration or maybe a failed deployment, I guarantee you the incorrect answer is almost always the one where a human being logs in to fix it.
You see, mature operations teams have this absolutely ruthless automation culture, and it's all built on one core operational philosophy. Every single manual action is a future outage just waiting to happen. Human beings get tired. Human beings skip steps at 3 in the morning when they're exhausted. Mature teams aggressively eliminate repetitive human tasks because manual intervention isn't a process, it's a liability. You should be using AWS Systems Manager Automation Runbooks to safely execute changes. You should be using event bridge rules, triggered by CloudWatch alarms, to fire off self-healing workflows. In a mature environment, treating manual SSH access as a standard operating procedure? No way. That is treated as a severe operational failure.
This mindset shift is just profound. It changes everything. A beginner sees themselves as a mechanic, waiting for the car to break down on the side of the road so they can pop the hood and wrench on it. But an operations engineer, they see themselves as an architect. Their job is designing an autonomous, self-healing factory.
So, remember earlier when I mentioned that single question elite operations teams ask before every deployment? It isn't, how do I build this? No. The question is, how will this fail? How will I know it failed? And how will it recover without me? Think on that. Because the ultimate goal of a cloud operations engineer is to engineer yourself out of a 3 a.m. wake-up call.